Good morning, everybody. Can you all hear me? I hope so. So welcome to day 2 of our virtual international conference on food digestion. So Maureen, if you can share our slides for this session. So thank you, Maureen. So we are now on day 2. So we're going to start this day with our live session from Australia and New Zealand, which will cover all topics. We will then move to session 5, which is on absorption models, session 6, which is digestive amylases and starch digestion, and session 7, which is in silico food digestion models and the gut microbiome. So we will finish by 2 p.m. Irish time. So I know it's the evening in Australia and New Zealand at the moment. So we do want you to join our Mentimeters. So tell us what country you're joining from. So use that code 49908218. And also we would like you to join our Mentimeter to ask you what subjects or topics you would like covered in our future webinars in food digestion. And that's a different code 16658213. Okay, next slide, Maureen. So just to summarize what we've done so far and what we will have succeeded in doing by 2 p.m. this evening, we have 57 abstracts from 4 different continents with 17 countries and 28 oral presentations from 13 countries with 22 PhD students. We had a great poster session last night, thanks to the Moore Park postdoc team, 24 flash presentations, lots of voting for the best poster, etc. We do have a book of abstracts, which you can find on our INFOGEST website or on LinkedIn. And we will be giving prizes at the very end for the best oral PhD talk and the best flash presentation. So the next slide. And of course, this is just an advertisement for the next conference next year, which is the 7th International Conference on Food Digestion, which will be in Cork, Ireland. So right now, I'm going to hand it over to the chairs of session 3, which is Alejandra, I'm really sorry about the way I pronounce your name, Asidofani from the Ridditt Institute, Harjinder from, of course, the Ridditt Institute as well, and Mike Gidley from the University of Queensland. So if you'd like to put on your cameras and unmute yourselves, you can introduce session 4.
Thank you very much, Linda, and good evening from the bottom of the world. We hope everyone is enjoying this conference, and it's a great pleasure for the Australasian community, Australia and New Zealand, to join in this virtual international conference. This is a topic area that there are many active researchers in the space in Australia and New Zealand. And so it's a great opportunity for 4 of our PhD students, so all 4 presentations will be by PhD students, to share with you some of the work that we're doing here and to give you some insight into the topics that are of interest in this part of the world. But before we get started on that, we have some advertising to do. And so you are not the only one to have a conference. So we are also organizing a virtual conference later in the year. And so now I'm going to throw over to Harjinder to give you a little bit of the background on a stream of conferences that has been run in this part of the world called Food Structure, Digestion and Health. And Harjinder, basically as the prime mover for these conferences in the first place, is the right person to tell you a little bit about the history of this conference. And then I'll come back and tell you about this year's events. So over to you, Harjinder.
Thank you, Mike, and greetings from down under as well. It's a bit later here in the evening, but still quite nice day to be able to, great to have this opportunity to be able to have this session and share some of the activities, especially from PhD student projects with you all. And as Mike mentioned, this whole area of connection between food structure and digestion obviously goes way back, and and the 2 conferences, food digestion and food structure, digestion, health, complement very nicely over many years. And it's actually, there's a lot of collaboration and activity that go between the different labs right across Europe, US, and Australia, New Zealand. So just to give you a bit of history of Food Structure, Digestion, and Health Conference, that actually started in Palmerston North, where Riordan Institute is based. That was the beginning of our new Center of Excellence in Food Structure and Digestion, and that was held in 2012. Then we formed a partnership with CSRO to jointly host those conferences from there on. So then 2 years later, we had conference in Melbourne, and then we moved back to New Zealand, to Wellington, then to Sydney, and then back to New Zealand to Rotorua. So I think many of you had attended these conferences. We had quite a few keynote speakers as well from this group in Rotorua, also in Wellington. So there's a very successful series of conferences over now many years. And obviously, this field of research is still growing rapidly, and a lot more to do. I think we have many more exciting discoveries to share in the future in this space. And the new one this year, we've been organized by CSRO in conjunction with the Riordan Institute. And now I will hand over to Mike to say a bit about the new program.
Thank you, Harjinder. I am hoping that I have shared my screen successfully, but please let me know if I haven't.
Yeah, it's lovely. I can see it.
Okay, good. Thank you. So as Harjinder was saying, we've had a number of conferences in the theme of food structure, digestion, and health, starting with the one that he co-organized in 2012, and basically every year or two since then. So the last one we had physically was in Rotorua in New Zealand in 2019. And so it was Australia's turn for the next conference, which was scheduled for this year. Clearly, because of where we are, that has to be a virtual conference. So this is basically to bring to your attention the fact that we will have a virtual conference in November. The website has gone live literally today. So this is hot off the press news. So please go and find it. Just Food Structure, Digestion, and Health will find you the website, hosted by the CSIRO. And the aim is to really foster collaboration across our disciplines that better deliver food and nutrition outcomes through understanding the relationships between food structures, their digestion, and health outcomes. So as a virtual conference, it is an opportunity for it to be much more international than it often has been. We realize that the tyranny of distance is a real issue with getting people from the Northern Hemisphere to visit New Zealand and Australia, but there's no excuse this year because we are all online. And so we are looking forward to be able to host this conference in November. You can see here the conference sessions. We will have a traditional arrangement. We've had this type of agenda over the last several meetings. So we'll start off on the first day with a masterclass of food and health, and then move through 3 topic areas on food structure design, microbiota, and future challenges for research. The way we're looking at this is probably about a 2 or 2.5 hour session each day. So it will probably be something around this time of day, possibly, or the other possibility is it will be in the early morning Australia time, the evening in Europe. So we'll work out those details and let you know. So we will open the call for abstracts soon. So please have a think about that. Please join us. There will be a small registration fee because we need to have some conference organization that we can't manage ourselves. So there will be a small registration fee, but we will make sure that everyone has access to all the materials once you register, recognizing that time is a real issue if we want to have a global conference. So we'll work through those details, but really look forward to welcoming as many of you as possible to this online conference to really pursue this really interesting topic area, that the intersection between the physical structure of foods, the way in which they get digested and fermented, and the health outcomes. So please look forward to that, and please do your best to attend this and let everyone else know as well. So we'll give more information on the website as the months go by. As you see, we have deadline for receipt of abstracts is not until September, so there is plenty of time to be thinking through what you would like to present, and we will have a combination of talks and posters, and you'll be able to find more details closer to the time. So with that, I think let me stop sharing that, and I think that's all the advertising I wanted to do. For those of you that come back that are still here at the end of the session, I will probably repeat the advert then as well if we've got a couple of minutes to spare. In the meantime, I think we're getting close to being able to start the session, but I'm aware that we're still a few minutes ahead of schedule. So yeah. I see Linda's on the line. Would you like to fill a bit of time in, Linda?
No, not at all, Mike. The conference looks very interesting. I just wanted to remind attendees that during the session, if they have any questions, to put it in the Q&A box so that the chairs can read it to the speakers after their presentations. That's all.
Thank you, Linda. So we have 4 presentations in this session. There are two presentations from PhD students in New Zealand and 2 in Australia. So I'm now going to hand over to my co-chair Alejandra in New Zealand, who will take you through the first 2 talks from the students from New Zealand. Over to you, Alejandra.
Thank you, Mike. Hello, everyone. It's a pleasure for me to introduce the speakers of this session that comes from New Zealand. Our first PhD student that will give a talk today is from the Reader Institute, Joanna Nadia, and she will be talking about the effect of food structure on starch hydrolysis during gastric digestion, starch enzyme, and glucose absorption in vivo. Joanna, the floor is yours.
Hi, I'm Joanna. I'm a PhD student at the Reader Institute in New Zealand. Today, I'm grateful for the opportunity to talk to you about the effect of food structure on starch hydrolysis during gastric digestion, starch emptying, and glucose absorption in vivo. Before we get into the details, I have one question. Can you relate with this? Or, let's be more specific, to starch. Starch is a type of carbohydrate, and why is it important in our daily diet? So when we eat something that is rich in starch, the starch will be converted to glucose in the small intestine, and the glucose is absorbed to the blood, circulated to different parts of the body to become the source of energy. As a result of this glucose absorption, we have changes in our blood glucose level after we eat. And uncontrolled changes in the blood glucose level like this are something that's called glycemic response. It is not desired because it has been related with different health problems such as type 2 diabetes and also obesity. As a result, there have been studies conducted to understand what factors that can impact glycemic response and how we can change the glycemic response or modify it. Some of those are food composition and structure and also the portion size. But we don't really understand how this food structure difference may affect the digestion processes, because it is true we have the food, but the food will be digested. So the structural breakdown of the food during digestion is important, as well as the delivery rate of material to be converted to glucose in the small intestine, which means just one step before the small intestinal digestion or the gastric digestion is important. Previous research has shown that different food structures had different gastric emptying rate or the rate of delivery of materials to the small intestine. And the relationship that was reported was that food with longer gastric emptying half time or lower gastric emptying rate had a lower maximum change in the blood glucose level, and the other way around. But we should understand as well how this gastric emptying rate may differ between different food structures, which may be impacted by what happens during the gastric digestion. So how does the stomach work? Functionally, the stomach can be divided into 2 different functional regions, the proximal and the distal stomach. When we have food bolus, which is a mixture of food that we chew with saliva, the food bolus will start filling the stomach from distal to the proximal stomach. And in the saliva, we have salivary amylase that can still continue digesting the starch inside the food as long as the pH is still maintained above pH 3. So we have these food bolus filling our stomach. At the same time, we also have gastric secretion that starts to be produced, and it starts filling the distal stomach going up to the proximal stomach. As a result, there will be this different biochemical environment because with more gastric secretion in distal stomach in the beginning, there will be less activity of salivary amylase. Also, the distal stomach had a more contraction compared to the proximal stomach. It has a higher force. Then the distal stomach can act as a grinder of the food particles. However, the proximal stomach has less contraction force compared to the distal stomach. As a result, food bolus that sits there will just stay right there with the remaining salivary amylase activity inside the food bolus. As a result of that, there will be the difference between distal and proximal stomach content, and it may impact the extent of the particles that are emptied to the small intestine, and it may also impact the glucose absorption later on. But we don't really understand how this may be related to each other and how it's affected by the food structure. As a result, the research question to be answered today is, how does food structure affect gastric digestion and glucose absorption of starch-based foods in an in vivo model? Meaning we include the physiological responses that we cannot see in vitro model. To answer the question, we had 6 test diets. They are from 2 different starch sources, durum wheat and white rice. They are all cooked, so they are high moisture systems. And 4 structural levels of the food were studied. Semolina, which is a porridge structure. We also have couscous and rice couscous, which are agglomerate structure. Rice grain, which is a cooked grain structure. And pasta and rice noodle, which is a noodle structure. And in a bigger picture, we can also classify these diets according to their differences in the macro and microstructural. So the first group is a less complex structure, which is a smaller size diet and also with less compactness of the starch arrangement in the food matrix. And the other group is a more complex diet, which has higher particle size and also more compactness of the starch arrangement in the food matrix. For example, here you can see in semolina, rice couscous, and couscous, we had some starch arrangement and with some pores in between or solubilized starch granules in the semolina. But for the more complex diet, we had more compact arrangement of the starch granules or the starch lumps in rice grain, pasta, and rice noodle. The 6 test diets were fed to growing pigs. And in the study, each pig was fed with 1 test diet. And after 30, 60, 120, or 240 minutes, we collected the portal fin blood sample. And after that, we collected the gastric digesta or the gastric content. From the gastric content that was collected, we analyzed the proximal and distal stomach separately for diameter and total starch content, which was used to calculate starch emptying rate in the whole stomach. We also measured the texture in terms of the hardness or the maximum force that's reached under compression test. And this is used to calculate the softening or breakdown rate of the food during digestion. We also measured the maltose content as a measure of the starch hydrolysis product in the stomach. For the portal vein blood sample, we analyzed the plasma for the glucose concentration. Right, let's get to the interesting part of the study, which is the findings. Just to remind you again, we have 6 diets here in the study. We have 2 big groups of structure, less complex and more complex. The difference between these diets are the particle size, where less complex structure had a smaller size, more complex structure had a bigger size, and the starch arrangement in food matrix in less complex structure is less compact, more complex structure has more compact starch arrangement in food matrix. And now let's see how they differ in terms of their emptying time. The starch emptying half time of these test diets were different apparently between the 2 groups, where the less complex structure had a lower starch emptying half time, but the more complex structure had a higher starch emptying half time, meaning that they are emptied slower. This may be due to the difference in the macro structure and also the microstructure. And also it's interesting to see that between these diets as well, and we can see a trend where it's an increasing trend between the macro structure and also between the increasing starch arrangement in food matrix. Can we really see any differences in terms of the gastric digestion, or let's be more specific, in the starch hydrolysis during digestion between these two diets? Because we hypothesized that less complex structure, because of their small particle size and also their less complex starch arrangement in the matrix, it will be easier to be mixed with the gastric secretion. And also it doesn't need that much breakdown to produce small particles to be emptied to the small intestine. So we expect to see minimum starch hydrolysis during gastric digestion. But for the more complex structure, we expected more chemical breakdown that's going on due to this remaining salivary amylase activity, because they are emptied slower, so there'll be more time for contact between salivary amylase and the food that's sitting in the stomach. So let's see here the comparison between the two groups in terms of how maltose is generated during the gastric digestion. And here I presented the result as the ratio between the hydrolysis product relative to available starch, or maltose relative to the starch available in the digesta. What you see right here is the comparison between the proximal and distal stomach digesta in terms of the ratio. And let's see, for the less complex structure, we didn't see any difference between the proximal and distal stomach content in terms of their chemical composition. And also at the longer digestion time, the composition was more or less similar, meaning that there was less changes during the gastric digestion due to starch hydrolysis. However, for the more complex diet, we saw what we expected. So we saw that in the proximal stomach content, we have a higher hydrolysis product relative to the starch available in the digesta, which indicate there might be some remaining salivary amylase activity that digested the starch further in the proximal stomach, because proximal stomach is less mobile, and also the food bolus can sit there for a longer time for the more complex diet. And in another study where we also look at the intragastric pH of these two different groups, the more complex groups actually has a higher proximal pH even until 140 minutes of digestion, while for these less complex diets, all of them had reached a low pH and homogeneous pH profile after 240 minutes digestion. So it implies that the complexity of the structure, which is the macro and the microstructure, contribute to the possibility of remaining salivary amylase activity in the stomach. And we look at the overall gastric digestion of the less complex versus more complex structure, we can also see that there's an accumulation in terms of the digestion of more complex structure from starch to maltose. So here we see that both diets were emptied over time, but at just a different rate, where more complex structure had a lower emptying rate. But when you look at the ratio between maltose to available starch in the complex versus more complex structure, it was quite interesting to see that for the more complex structure, it initially decreased, but it increased over time. But for the less complex structure, we had a decrease, and then it reached around a plateau value, which may due to the to homogeneous mixture of the digesta between the proximal and distal stomach digesta. So in the end, what was emptied was a homogeneous mass, and there is no more further chemical changes. But for the more complex structure, because there was this generation of maltose in the proximal stomach, although the starch was emptied over time, we also have more maltose available due to this remaining salivary amylase activity, and it increased over time. Next, we also want to see if there's any difference in terms of the absorption of the glucose to this portal vein as affected by the food structure. So we try to get a parameter that is able to describe the absorption characteristics of the different diets. So that's why we did the data analysis as a cumulative fraction. And this data actually fit well to Michaelis-Menten kinetics model, which is a model that's been used to model drug absorption kinetics. And there are two parameters that are important in this equation: the Vmax, which is the maximum concentration of plasma glucose that can be accumulated, and Km, which is the time needed to reach 50% of the accumulation. We also did the same approach to get this Vmax and Km later on in the comparison between hydrolysis product relative to available starch in the stomach. So what are relationships that we can see from the data? First, let's see how the difference in the food structure may affect difference in the starch emptying half time and also accumulation of hydrolysis product in the stomach. Apparently, as we have more compact starch arrangement in the food structure, regardless of the complexity of the group, of the complexity of the diet group, if you remember the less complex and the more complex structure, we see a consistent trend where more complex structure had a higher starch emptying half time and as a result, higher hydrolysis product accumulation in the stomach. This may be due to the slower mixing between the diets with the gastric secretion, which gave the opportunity for remaining salivary amylase to continue. How about the effect of food structure on the portal vein glucose absorption? So here we can also see a trend where in general, when we have diets with more compact starch arrangement, we had less portal glucose maximum accumulation. This may be due to the higher emptying half time or the lower delivery rate of materials from the stomach to the small intestine to convert the material into glucose. And it means that there will be less glucose available for absorption. And as a result, the accumulation of glucose will be less for diets that have less materials to be converted to glucose in the small intestine. It also may mean that whatever that's been converted will be disappearing quickly as a result of less material that is available in the bloodstream. Now, can we also try to find a relationship between how the food breaks down in the stomach and the effect on the portal glucose absorption? The answer is probably. Right here, we see that food with different gastric softening half time had different portal glucose accumulation rate. Although the trend was with more complex starch arrangement, we have higher gastric softening half time or lower breakdown rate. It doesn't necessarily mean there is a certain trend apparently between the 6 diets, but we can see a clustering between the less complex and the more complex diet. In the less complex diet, we see that as the compactness of the diet increase, we see an increasing softening half time, but a lower portal glucose accumulation rate. On the other hand, for the more complex structure, again, we still see an increasing gastric softening half time with increasing compactness of starch arrangement and also increasing macrostructure, but there was an increasing also in the portal glucose accumulation rate. And if you want to use this knowledge to food structuring strategy for a desired control properties and also absorption properties of glucose, we need to look at the data together between the glucose accumulation rate and also the maximum accumulation that can occur, because I think that they may impact the overall glycemic impact later on of the food itself. So to sum up, the key findings from the study are, first, that starch hydrolysis can occur in the stomach as a result of remaining salivary amylase activity. It most likely happen in the proximal stomach. But it is important to remember that everything depends on the food structure, where we remember the more complex structure had this remaining salivary amylase activity in the proximal stomach, but not for the less complex diet. It means food structure has a role on gastric digestion, gastric emptying, and portal glucose accumulation. And what I mean by food structure here, to be specific is difference in the macrostructure or the particle size, and in the microstructure, which is the starch arrangement in the food matrix. And finally, from what we already gathered until now, and we're still looking forward to understand better what's going on during the digestion process, we can also say that, in general, less compact starch arrangement in the food matrix will result in higher gastric breakdown rate, higher starch emptying rate, and less accumulation of starch hydrolysis product in the stomach, and higher accumulation of portal glucose. And hopefully, as we understand better later on, we may be able to apply this understanding for food structuring strategy for controlled glycemic response. For that, that's my presentation. Thank you so much for listening, and I would like to acknowledge my supervisors, the Reed Institute Nutrition team and Food Engineering team, and all of the lab managers that whose lab I work in the Massey University. Thank you.
Oh, well, thank you so much for that presentation. It was very well put together. So I can already see there's a couple of questions on the Q&A box for you, Joanna.
Yes.
So the first one is, Is there a difference in protein content between less or complex foods, protein buffer pH, and allow amylase activity?
Okay, thanks for the question. So the protein content difference is mainly between the wheat-based and the rice-based foods. And yeah, it means also it affected the buffering capacity of the diets. But we actually just published a paper in Food and Function about this, like the initial part of the pig study, and we reported that the buffering capacity may impact a bit of this behavior of the less complex foods, but it's not as much as the initial macrostructure of the food and also the breakdown rate. But yeah, they do have a difference. If that's the short question, the short answer.
All right, thank you. Yeah, someone saying here, a very interesting talk. How did the different food structure affect gastric juice secretion rate and amount? And did you observe any difference there?
Okay, this is also something that we put in our recently published paper in Food and Function. So we tried by doing some mass balance approach, we tried to estimate the gastric secretion between the different diets. And it is interesting to see that for semolina, which had the porridge structure, the buffering capacity doesn't seem to affect the secretion rate. While in the past, we know that food buffering capacity might impact the gastric secretion. But for the other diets, we can see an increasing gastric secretion addition as the food buffering capacity increase. Yep, so that's the answer, I think.
Yes, I'm reading a comment here from Didier Dupont, very nice talk. Probably I missed the information, but were the meals isocaloric?
They were not like really isocaloric, but they were quite similar because we tried to standardize the starch content, and we also look at the type of starch that's quite similar in terms of their amylase and everything about the chemical composition. So it is not very isocaloric exactly, but almost. But you don't really see any differences as well in the gastric emptying rate as affected by the calorie content of the meals.
Great. The levels of endogenous glucose during digestion time were considered in the measurements. So this doesn't mean the natural elevation from hormonal response. Congratulations for the research. It was much interesting.
Thank you. It's great input. We didn't really measure the endogenous glucose because of the limitation of the design of the study. But even in the model itself, because we did this kinetic modeling, I only fit the 4 different points that we collected, and I didn't specify that at time 0 there was no glucose or anything else. But interestingly, without doing this consideration of endogenous glucose, we still see a trend. But maybe that's something that we can see also in the future.
Okay. I think we have 2 more minutes to complete the questions. So I'm going to probably read the other 1 or 2 questions, and the rest you're welcome to answer them afterwards.
Thank you.
So what's the difference? Was there a difference in the amount of swelling, difference in particle size distribution, evolution in the stomach?
In terms of the swelling, we didn't really measure that, but we also measured something that we call as the saturation ratio, if that can maybe be related to the swelling of the diets. So that's basically the absorption of the water to the diets relative to how much water that can be absorbed by the diets in the maximum capacity. And we could see some of this saturation difference in the saturation ratio and also in the particle size distribution. And it's in the paper that we published. So I'm promoting my paper that's recently published in Food and Function.
All right. Yes, so I think I'll leave it here. You still have a couple of questions. Thank you so much for the presentation and your answers.
Thank you,
so
Anna.
we are having problems with the second speaker from New Zealand. Some IT programs are related. So I think we can move to the Australian based speakers and then see if we can get the second New Zealand speaker on board at the end of this session. Thank you so much.
Thank you, Alejandra.
I hand over to you. Yes.
Thank you. So it's my pleasure to introduce the first of the Australian talks from my colleague at the University of Queensland, Dong Dong Ni. and his title is Exploring Relationships Between Satiation, Perceived Satiety, and Plant-Based Snack Food Features. So if we could run the presentation, please.
Good morning, everyone. I'm Dong Dong from the University of Queensland, Australia. Today, I would like to share a story about exploring relationships between satiation, perceived satiety, and plant-based food features. First, I would like to give you some background about the satiation and satiety, as well as why we are studying on this. Actually, both satiation and satiety are the feelings of fullness. The difference is satiation is the feeling during eating, which can stop you eating, whereas the satiety is the feeling after the meal, which can stop you to look for food. As why we are studying on this, let's look at the picture on the right here. As we all know, obesity is quite severe worldwide, and the main reason for the obesity is overfood intake. And we would like to manipulate our fullness, satiation, satiety to control our food intake, which can help us to manipulate our body weight as well as the obesity worldwide. As food scientist, I would like to zoom into food features impacting on satiation and satiety. There are many papers focused on this area, and I concluded 4 main types, including the sensory, physical property, and nutrients and energy. For example, the food structures, like the plant-based food, they have the cell wall structures, which will affect on the satiation and satiety as well as the food intake. As to the nutrients, there are many studies focusing on the high-fat diet, high-protein diet, high-fiber diet, has the stronger and longer satiation as well as the satiety. Now, what is our approach? First, we select 6 types of plant-based foods, including the apple, banana, carrot, avocado, chickpea, and the macadamia. These 6 types of food are plant-based food. They have the plant cell structures. The cell wall structures we should here is labeled blue, and the nutrients were encapsulated here in the cell wall. As why we select these 6 types of foods, there are some comparisons here. As the apple and the carrot, they are the sugar-rich food, and the banana and the chickpea are the starch-rich food, and the macadamia and avocado are the lipid-rich food. And in the same type of nutrients, there are some comparisons in the different type of the cell wall, the strong cell wall and fragile cell wall. Then we recruited the participants to do our experiments, including 2 parts. The first part is the ad libitum food intake experiments. And in this part, the participants will be served the test food as the mid-morning snacks for 20 minutes. And in these 20 minutes, the people can eat as much as they can until they feel comfortably full. And during eating and after the meal, up to 3 hours, they will tell us how full they are through the questionnaires. And the second part of experiment is our oral processing measurements. The participants will be served the test food and then tell us the number of chews they used for each type of food. And after the experiments, All the results, including the satiation, satiety, food and energy intake, and all the food features were collected and we put together, try to analyze the relationships between satiation, satiety, and food features. Now let's see some results about the perceived fullness during and after meal. During the meal on the left, we can find the apple and banana has the highest fullness, and whereas in the after the meal, the fullness has a large variability in food types we can find. In the different nutrients, the sugar-rich food like the carrot and apple has the lowest fullness, whereas the lipid-rich food like the macadamia and the avocado has the highest fullness compared with the sugar-rich food. And the higher energy dense food like the macadamia and the avocado has a higher fullness. And in the same type of the nutrients, the strong cell wall food has a higher fullness. The carrot is stronger, has a higher fullness than the apple. The macadamia has higher fullness than the avocado. The chickpea has a higher fullness than the banana. And when we look this picture in this way, as the red line here, if the people started to eat the next meal at the same level of fullness, as we can see here, the avocado could be 1 hour later than the apple or carrot. This is quite surprising. Then let's see some results about the food and energy intakes here. Let's see the picture on the left. We can find in the same type of the nutrients, the strong cell wall food will have significantly lower food intake than the fragile cell wall food. We can find the carrot is lower, significantly lower than the apple. The chickpea is lower than the banana. The macadamia is lower than the avocado. Let's see on the right here, in the energy intake, we can find between the different nutrients type, the lipid has significant energy intake than the starch. Then the starch is significantly higher than the sugar. Of course, the higher energy density will lead to the higher energy intake here. Now, when we put all the variables together, we use the principal components analysis as well as the Pearson correlations to analyze them all together. And then we find 3 points. The first point is the plant food factors that affect the perceived fullness during and after eating are differently. And we can find the satiation and satiety, they are negatively correlated here. And the second one is the energy factors of the food has no business with the satiation during eating, but it is positively correlated with the satiety. And we can find the PCA plot here. The satiety is more close to the energy density, fat, proteins, and they are all together. And the last one is the number of chews is correlating negatively with the satiation, but positively with the satiety. And this is very interesting, and we would like to explore more reasons behind this. So we find both the individuals and the food types affect the number of chews. Let's see on the picture on the left. The individuals shows big variability in food oral processing, the number of chews. We can find the highest person is much higher than the lowest person here. It's almost a 5 times difference. And when we look at the picture on the right, it shows the number of chews had large variations with plant-based food types, for example, the carrot and the banana. And we can find here the strong cell wall food has need more number of chews here. We have tested the correlations between the number of chews and the satiation and satiety. They are correlated, so we did the linear regression models between the number of chews and the satiation, number of chews and the satiety. The R-squares here shows there are very strong relationships between the number of chews and the satiety. Then the number of chews affect on food particle size and the digestion rates. We can find here on the picture on the right, the low chew has large particles, but the high chew has only small particles and it's more homogenized. And the particle size distribution also shows the similar result here, and the high chew has no large particles. And we also did the digestion rate in the different number of chews. We find the high chew, around 120 chews, they are about 15% more digestion rate than the low chew, 20 times. And we also find the number of chews not only affects on the total digestion rate, but also the speed of the digestion. We can find here the high chew is about use the less time to reach the same level of the starch digestion rate here. And all these can affect on the total nutrients release and the different releasing time and the location in our digestion tract. And all these things can affect on our fullness after the meal, the satiety. And the pictures here shows the foods after chew, before digestion, and after digestion. We can find here the starch is labeled as green and the cell wall is labeled as blue. We can find the number of chews not only affects on the food particle size, but also can affect on the different intact degree on the cell wall structures, which also explains why the high chew has a higher total digestion rate as well as the speed than the low chew. And all of these things can contribute to the satiety. Now let's summarize. We find the 3 key points. The first one is food factors, especially the energy and oral processing effects on the fullness during and after eating are different in plant-based foods. And the second point is energy density, nutrients, and the cell wall type have significant influences on food and energy intake in plant foods. And the last part is the number of chews affect on food particles and digestion is associated with the satiation and satiety variations. And further, we would like to explore more foods and food features like the texture and sensory together to get a more complete picture of the food factors affecting on appetite. And basing on all these results and these kind of experiments, the portion size design and the meal frequency recommendation for specific plant-based foods could be made. At last, I would like to acknowledge all my advisory teams and all the people who helped me before. And thank you for listening and waiting for your questions. Thank you.
Thank you, Dong Dong. Please unmute yourself, and I have some questions for you. So we have 3 questions already. Please, people, put the further questions in the Q&A box if you're interested in asking Dong Dong a question. First question is about some work from around the turn of the century around the satiety index. I'm not sure whether you're familiar with this, but the question is, how does the relative satiety of the foods that you've looked at compare with the satiety index from many years ago?
Thank you for the question. Actually, the satiety is a very subjective thing, so it has a very large individual differences. So there is a satiety index. It's a kind of just put a very subjective things into a quantity. So and in my experiment, our experiment, we used a different way to measure our satiety or satiation. We use the slope of the fullness. So it's quite different with the satiety index. I think it would be interesting if we use their way to measure the satiety index to measure our plant-based food and compare the results.
Thank you. Another question from Caroline Orfila. Really, what she wants to understand, what do you mean by a strong versus a fragile cell wall? What characterizes it? What are they? How are they related to the tissue hardness and cohesiveness?
Actually, the strong cell wall versus the fragile cell wall. That means we didn't measure the hardness or the texture of our food. But from the texture, that just feels like the strong cell wall, the microstructure of a strong cell wall can make our food have a harder food. It will be a hard tissue food, and the fragile food will be a kind of the softener, and the cell wall will be fragile. And I think it will be interesting to consider further to consider the texture of the food and then put them inside and then to analyze all the variables together and to see the texture effects on the satiety or effects on the satiation or the food intake. And that's a further direction, I think.
And then the next question is sort of related. So it's saying, how do you think of hardness as a factor? Is hardness a good measure as well as cell wall type? And I guess you've sort of answered that, but what do you think should be the right measure here that gives us an index of the different behaviors?
Sorry, which question?
So this is from Rujan Deng. Have you measured the hardness of different foods? How do you think of hardness as a factor compared to the cell wall type?
Thank you for the question. Actually, I just answered before. We haven't measured the texture of our food, and I think it's an interesting factor. The texture of food we can analyze later.
A question from Didier Dupont. First of all, great talk. Thanks, Didier. Do you think that ultra-processed foods that do not require intensive oral processing would lower satiety and increase food intake?
This is a very good question. The ultra-processed food will don't need a very strong or longer oral processing. That can lead to from the sensory view or the kind of the sensory view, the satiety is a very comprehensive feelings. It comes from the many signals we put together and to get a feeling of satiety. If we have less or lower oral processing time, will give us a weak sensory feelings, so it can definitely affect on our satiety, but I'm not sure.
No, okay, so that's it's a difficult one to answer, that one, yes, because I guess that some of the factors you saw were also about the macronutrient content rather than necessarily the food structure. So there's a range of effects there, isn't there? I think the final question to keep us on time from Miriam Grundy, what about the porosity of the cell wall among the different foods?
Porosity of the cell wall among different foods. The different foods have a kind of because they have they comes from different plants. The cell wall is quite different, but we have to categorize it into a strong cell wall or fragile cell wall. It's a kind of relative thing. We cannot compare the food like this sometimes, but in our experiment, we just give some directions for further.
Okay, thank you. Finally, there was just one more question now, just a technical question about the confocal microscopy. Can you recall how did you label the starch and the cell walls?
Oh, we use the fluorescence, FITC, and just put it into the laser and it will show up, and it is very need experience.
So that was for the starch, I think, was FITC, and then for the cell walls, the different. Did you use calcofluor for that?
Yes, calcofluor.
Okay, thank you very much, Dongdong. We have to move forward, so if there are any further questions, keep putting them in there and Dongdong can answer them online. And thank you. We'll move on to the next speaker. For those of you who are looking at the program and thinking we're not at the right time, we had some trouble trying to find the second speaker. So we're hoping that maybe they can come on at the end of the session. So that's Nadisha Dirukci. If they become available, then they will come on after the next speaker. But now we'll move on to Wei-Yan Xiong from Monash University in Melbourne, Australia, and a talk on the structural features of intact cells in controlling the rate and extent of digestion in trapped macronutrients. So if we could run his presentation, please. Thank you.
Hello, everyone. I'm Wei-Yan Xiong, a PhD student from Monash University. I feel very glad to give the presentation here to introduce the previous research of our group. The title of my presentation is Structural Features of Intact Cells in Controlling Rate and Extent of Digestion in Trapped Macronutrients. And our research is mainly focused on the starch of whole host cells. Whole is a nutritive food because they are very low in fat and high in carbohydrate, protein, and fiber. According to the definition of the resistant starch, the starch of whole host food belongs to the type 1 resistant starch, which is physically inaccessible to digestive enzymes. Therefore, consumption of whole host food is proved to have distinct health benefits. For example, lowering glycemic index and reducing the risk of some chronic diseases. And in order to investigate the health effects of whole hosts, a method of isolating intact host cells were introduced to establish the whole food model. After the raw poses or cooking under excessive water, the cell wall will be softened. And after meshing and sieving process, the intact host cells are easily obtained. From the microscopic observation, we can see that the macronutrient, for example, the starch and the protein, are enclosed in the cell wall. My presentation will be divided into two parts. The cell wall modulates starch digestibility, and processing conditions modulate cell wall permeability. There are three mechanisms for cell wall modulate starch digestibility. The first is that the cell wall can limit swelling and gelatinization of starch granules. With the protection of cell wall, the crystalline structure can be partially retained after experiencing high temperature cooking process. And the second is the cell wall can restrict enzyme diffusing into the cell, thereby hinder the enzyme accessing entrapped starch directly. And the third one is the enzyme can bind to cell wall components to lower the starch hydrolysis. And when the cell wall protection layer is damaged, the starch digestion extent and rate will increase drastically, but the starch digestibility of broken cells is still much lower than the starch counterparts. And sometimes, the cell wall will be damaged by processing, and the permeability of cell wall will vary from different processing conditions. Okay, let's see how the cell wall restricts enzyme diffusing into the plant cell. First, it is a confocal image of chickpea cells hydrolyzed with FITC labeled alpha amylase for 4 hours. For this picture, we can see that even after 4 hours hydrolysis, the enzyme still concentrated at the outer periphery of the cells, but cannot penetrate into the cell because of the hindrance of the cell wall. And combined with the result of the starch digestion, we can know that the starch digestion extent and rate of intact cells is much lower than the broken counterpart with the protection of cell wall. And from the other research, we use the amylase size FITC to simulate the diffusion of the enzyme. It is showed that the amylase size FITC cannot get into the cell wall because the pore size of the cell wall is too small. And from the result of starch digestion, the starch digestion extent and rate of pinto bean cell is extremely low when compared with the purified starch. So, it is evident that the cell wall can hinder the enzyme diffusing into the cell effectively. Next, let's see how the cell wall limits swelling and gelatinization of starch granules. In this research, pinto bean cells and starch were cooking under 95 centigrade for 1 hour. First, we can see from the microscopic pictures, the pinto bean cells even be treated under high temperature. The cells are still intact. And because the space is limited by the cell wall, the swelling starch granules are compactly entrapped in the cells. And from the polarized light microscopic picture, we can see that the entrapped starch still have high birefringence intensity, and even some distinct maltose crosses can be observed. However, for the starch sample, because the starch are almost fully gelatinized under such condition, so the starch granules are fully swelling and formed hollow granule ghosts, and almost no birefringence can be observed. And the result of X-ray diffraction is consistent with the microscopic observation. The relative crystallinity of pinto bean cells, which is 14.6%, is much higher than the pinto bean starch, which is only 4.7%. It is proved the entrapped starch owes more ordered structure than the purified starch. And with the cell wall can restrict the diffusion of enzyme as well as the cell wall can limit the swelling and gelatinization of entrapped starch. The starch digestion extent and rate of the pinto bean cells is much lower than the pinto bean starch. We're going to see the third mechanism for cell wall restricted starch digestion, the non-specific binding of enzyme to cell wall component. When we use the FITC labeled alpha amylase to hydrolyze the broken chickpea cells, we can see from the confocal images that the FITC labeled alpha amylase is not only binding to the starch, but also binding to the cell wall fragments of broken chickpea cells. And when we add in the cell wall fragments to the starch, from the progress curves for starch hydrolysis, after adding cell wall components, the starch hydrolysis is decreased markedly. And with more cell wall components were added, the lower the starch hydrolysis was. So it is evident that the alpha amylase not only binds to its preferred substrate, starch, but also shows strong binding affinity to cell wall components, therefore hindering the hydrolysis of starch. To investigate the effect of processing conditions on cell wall, the cells were isolated by 3 different methods. The first is 100 centigrade pressure heating, and the second is 80 centigrade cooking, and the last is the acid-alkali treatment. And the cell wall permeability was investigated with different molecular weight of FITC probes. From the confocal light scanning microscopy, for the pressure heating samples, noticeable fluorescence can be detected within the cells for 3 molecular weight FITC probes. And for 80 centigrade cooking sample, the FITC probes over 115 kilodalton molecular weight could not penetrate inside the cell. Only weak fluorescence is detected inside the cell walls by the 17 kilodalton FITC. However, negligible fluorescence is observed within the cells isolated with the acid-alkali method for 3 molecular weight of FITC probes. Overall, we can know that the cells isolated by pressure heating owe the highest cell wall permeability, and the cells isolated by acid-alkali treatment owe the lowest cell wall permeability. From the X-ray diffraction and thermal properties among 4 samples that were all cooked under 100 centigrade, we can know that the starch crystalline structure of 100 centigrade pressure heating sample is more ordered than other samples. In general, it will be more difficult to be hydrolyzed by amylase. However, the starch digestion extent and rate of it is much higher than other samples. It indicating that the high pressure treatment damages cell wall permeability and makes the enzyme is easier to access the entrapped starch. And when compared the starch digestibility between intact cells and broken cells of pressure heating samples, the starch digestion extent and rate of intact cells is still lower than the broken cells. It is evident that even though the cell wall permeability is damaged by pressure heating, it also can provide a partial barrier for enzyme diffusion. In other research, the pinto bean cells and starch were modified by heat moisture treatment. Compared with a native sample, the total relative crystallinity increased first, then decreased, with the moisture content increasing, because the disruption of crystalline structure and rearrangement of starch molecules occurred simultaneously during heat-moisture treatment process. And the stable crystalline structure can survive after cooking. The digestion extent and rate of native starch is the highest. And the heat-moisture treatment sample treated under highest moisture content will be the lowest. However, the starch digestion result of the cell is contrary to the starch. It means for cell samples, the starch digestibility is not dominated by starch structure. To investigate the cell wall permeability of heat-moisture treatment cells, we used the amylase-sized FITC to simulate the enzyme diffusion. Surprisingly, no internal fluorescence can be detected within native cells, but distinct fluorescences were detected within the cytoplasmic matrix of all heat-moisture treatment cells. It means that the heat-moisture treatment process can result in the damage of cell wall permeability. And combined with the result of in vitro starch digestion experiment, we assumed that the damage of cell walls may aggravate with the moisture content increase in heat-moisture treatment process. Today, we have talked about the pore cell wall can limit starch hydrolysis by 3 mechanisms. The first is that the pore cell wall can directly control the digestibility of entrapped starch by forming as a physical barrier to hinder enzymes accessing starch. And the second is that the pore cell wall can limit starch swelling and gelatinization during cooking under excess water conditions. And the third is that non-specific binding of alpha amylase on cell wall also can hinder the hydrolysis of starch. And we also discussed about food processing can damage the cell wall permeability. First, some extreme thermal treatment, for example, the pressure heating and moisture heating treatment, will damage the permeability of cell wall. And although the processing will damage the cell wall, pore cell wall still can provide a partial barrier for enzyme diffusion and limiting the hydrolysis of macronutrients. In the future, I think we can add the intact plant cells as a natural nutritional ingredients to other food and conduct in vivo experiment to study how does the intact pore cells affect glycemic and metabolic responses in humans. Furthermore, we also can investigate that how does the intact cells increase colonic health after they are sent to the colon. And more information about my presentation can be found in these articles. And last, thanks for your attention.
Thank you very much, Wei Yan. Can you please come on the screen? We have some questions for you.
Okay, hi.
Hi, so a first question from Caroline Orfia. Very interesting talk. Her question is, do you know how hydrated are the cell walls in either the dry or the cooked pinto beans?
Actually, we didn't focus on the cell wall, but we use intact pinto bean cells to do our experiment. So we just analyze the water content of the cells, but not the cell walls.
Okay, so the next question is sort of related to that is how did you isolate the native pinto bean cells? So what was the method that you used?
Actually, it's a good question because in my presentation, I showed that how we isolated the cooked pinto bean cells because I think the heat, like the boiling, can soften the middle element and the cell wall, so we can easily isolate the intact cells after boiling. But to extract the native pinto bean cells, sometimes we need to add some sodium bicarbonate and sodium carbonate to accelerate the softening and the swelling process.
Okay, thank you. So I have another question here. I'm not sure whether it was for you or for Dong Dong, but I think you can probably answer it. It says, can cells be broken up when we chew, or is chewing just breaking the food into smaller particles? So it's the only way to break up intact cells to cook or to process food. So do you think that when we chew food, we will break cells?
Actually, I think whether we can broken up the cells when we chewing is based on the tissue of the cell. Sometimes some plant cells, because it has stronger tissue, it will retain mostly intact after we chewed. But for some fragile tissue food, like some baked beans or baked peanut, it will easily be broke when we chewed. And sometimes, like the Dong Dong said, if we chew the food for a short time, the particles will be bigger and it will consist of many intact cells. And if we choose the food for more times, it will be broken into smaller particles, and so that the cells will be more likely broken when we chewed. And I think the cook or processing, for the pulse, I think it is hard to break the pulse cell tissue when we cooking or during some food processing, because I think the pulse cell structure is much stronger than other plant food. For example, the cereal the pulse cell is more stronger than the cereal food. Yeah.
Okay, thank you. Very comprehensive answer. So thank you very much for that, and thank you for all the questions. If there are any more questions, please put them in the Q&A, and Wei Yan can answer them directly by typing in online. But now I'd like to hand over back to Alejandra to introduce the final talk in this session.
Thank you, Mike. So our last speaker of this session is Nadisha Dilruski. Unfortunately, she won't be available for the Q&A session as she's having some IT problems to connect. But you're welcome to send her questions to her email, contact her directly. You can find her email on the Book of Abstracts. So from now on, we're going to play her presentation, and yeah, you're welcome to enjoy it.
Hello everyone. Before I start my presentation, I want all of you to think about a particular question. How often do you have ready-to-eat snacks? The habits of modern life are characterized by intense work and limited personal time. This has led to consumer eating habits are shifting away from the traditional 3 main meals per day toward more frequent snacking. Additionally, young people globally are attracted to ready-to-eat snack products because of their taste and ease of consumption. Because of this reason, global snack market is expanding at a dramatic rate, and it is expected to continue in future too. But the concern is most of these ready-to-eat snacks are made from refined cereal flours and they are rich in carbohydrates, low in protein, fiber and bioactive compounds. Therefore, these snacks are considered as high glycemic foods with low nutritional value. With the growth of healthy and sustainable diets and with increased awareness of the consumers about the link in between their diet and health, there is a big demand for development of novel healthy snacks. To fulfill this gap, there has been a number of researches carried out by combining different plant and animal sources to enhance the nutritional profile of snacks. With the aim of contributing to fulfill this gap, my study also focused to develop a ready-to-eat snack with a new combination of food sources and assess the effect of exclusion on nutritional, functional, physicochemical and sensory properties. In here, we have selected rice. Rice is a cereal and it is selected due to its color, flavor, hypoallergenicity, bland taste and better processing characteristics. Cowpea. Cowpea is a food legumes cultivated in Asia, Africa, Latin American countries, and it is a rich source of protein and fiber. Dietary fiber and resistant starch play an important role in human health by reducing the constipation and decreasing the risk of non-communicable diseases like CVD and diabetics. In addition, this dietary fiber acts as a functional food and used in weight control diets due to its low caloric value. Cowpea is a good source of polyphenols too, which are well known for free radical scavenging activity and preventing oxidative stress. Phytic acid and trypsin inhibitory activity, these are considered as anti-nutritional factors which reduce the bioavailability of protein and minerals. But there are recent evidences these factors reduce the carcinogen-induced transformation and it has anti-inflammatory and anti-cancer properties. And also the raffinose series oligosaccharides. Raffinose, stachys and verbascose are the main oligosaccharides considered as raffinose series oligosaccharides in cowpea. They are called as alpha-galactosides too. These alpha-galactosides from pulses are causative agents of flatulence in humans. Because these oligosaccharides are not digested by humans, since the intestinal mucosa lacks the hydrolytic enzymes alpha-1,6-galactosidase, microflora in the lower intestinal tract metabolize these oligosaccharides and produce large amount of gases like carbon dioxide, hydrogen and methane. Accumulation of these gases in the intestinal tract results in discomfort, pain and diarrhea-like conditions. But however, it is well known that the balance of intestinal bacterial flora is important, which could dominate the pathogenic organisms, thus improve the human health. There are recent evidences these galacto-oligosaccharides facilitate the growth of intestinal bifidobacteria. In fact, many prebiotic oligosaccharides are used in ingredients in various products. Then the whey protein concentrates, in here we use it as a secondary ingredients to improve the protein contents. Let's move to the methodology. These three ingredients are combined with 5 different ratios and rice used as the control. The in vitro enzymatic digestion was performed to mimic the gastric and pancreatic digestion. These in vitro studies on starch digestibility of foods provide an important data in initial screening of predictive glycemic response of food. Hydrochloric acid and acidic pepsin were used to mimic the stomach digestion. Small intestine digestion was mimicked by using pancreatine. Throughout the process, temperature was maintained at 37 Celsius and the reducing sugar content was analyzed by using the dinitrosalicylic acid method. Let's move to the results. These figures show the variation in release of glucose in raw materials and extruded snacks. As you can see, exclusion significantly increased the in vitro digestibility of starch. This could be explained by the loss of structural integrity of starch granule due to increased shearing action and kneading in the extruder barrel, which is ultimately increase their susceptibility towards enzymatic attack. And also extrusion reduced the particle size compared to the raw materials, and also it could be attributed to the higher degree of starch gelatinization too. It was noticeable that there was continual decrease of reducing sugar released with the increased level of cowpea and whey protein concentrate in both raw and extruded samples. This could be attributed with increased dietary fiber fractions with more cowpea substitution in formulations, may be led to changes in protein starch matrix, as well as potential encapsulation of starch by protein fractions, which reduce the enzyme hydrolysis. And the high water binding capacity of dietary fibers also reduce the starch digestibility of the extruded snacks. Further, the higher the contribution of resistant starch content in the extruded snack could be attributed to the low glycemic load by diminishing the availability of amylolytic enzymes. This fact is further illustrated by this bar graph, which shows the average incremental area under the curve values after 2 hours for raw and extruded samples, as determined using the in vitro procedures. It was noticeable that there was a significant reduction in overall amount of glucose release with increased inclusion levels of cowpea and whey protein concentrate in both raw and extruded samples. For instance, addition of legume flours, cowpea, in between 10 to 30% and whey protein concentrate 5 to 20% in rice-based formula reduce the 12 to 40% of reducing sugar release in extruded snacks compared to the control sample. This may be attributed with the increased proportions of cowpea and whey protein concentrate. The ratio of carbohydrate to protein is reduced in formulations compared to the control. And there are recent research evidence showed that this reduced ratio of carbohydrate to protein is helpful in weight loss diets and glucose management. In conclusion, the results obtained in this study demonstrated that the blends based on legumes and rice can be a novel combination in the production of expanded gluten-free snack with low glycemic load. And the high temperatures used in extrusion cooking will reduce the anti-nutritional factors present in legumes. And also, this research responds to the growing interest of consumers to find new healthy products with sustainable consumption of crops. These are references. Thank you very much for listening.
All right, so we're here back. Fortunately, Nadisha was able to join while her presentation was running. So we have here, you're welcome to post your questions in the Q&A box from now on, and she will be happy to answer. Otherwise, as we said, you're welcome to contact her by email. So if you have any questions, learning questions right now, please pop them in the Q&A box, and we'll happy to handle to her. Otherwise, we can close the session, and you can contact her directly. All right, we'll wait a couple of minutes. No questions coming. Thank you so much. So I will hand over to Mike. He will have a few closing words of our Australia and New Zealand session. Thank you so much for listening and for being here. Mike, I'll hand over to you.
Thank you, Alejandra, and thank you so much to our 4 presenters, to all PhD students, and all did an excellent job, I think you'll agree. So it's been a great honor to be able to join you today. I hope that we can do many more of these types of events that gets over the 9 or 10 hours time difference that we enjoy between our countries. And I'm just taking the floor back again just to further provide some announcements. For those of you who are here at the start, you will have seen this already, but we have quite a few more people who joined us from the beginning. So just to say again that we have a tradition in Australia and New Zealand of hosting a conference entitled Food Structure, Digestion and Health. It was first run from the Ridet Institute in the University of Massey University, where Alejandra and Harjinder are from, in Palmerston North in 2012. And then every 1 or 2 years since then, we've run a conference alternating between Australia and New Zealand. So the last one was in the wonderful city of Rotorua in New Zealand, next to all the geysers, and a fantastic scientific and enjoyable social occasion. Unfortunately, of course, this year we can't do that physical meeting in the way that we would like to, but I'm here to let you know that we will have an online conference. So Food Structures, Digestion and Health 2021 will be a virtual conference. It will be on from the 16th to the 19th of November. The conference website has just been launched, so just search for Food Structure, Digestion and Health and you'll find it. This will be hosted by colleagues in CSIRO Australia in conjunction with Ridet Institute in New Zealand. And the aim here is to establish collaboration across disciplines with the aim of using our knowledge of food structures and digestion to improve overall human health. We will follow a session arrangement that we've found has worked previously, but we'll do this in concerted 2 or 2.5 hour blocks. So at a single time to try and suit as many people around the world as possible. Quite possibly this will be an early morning Australia, New Zealand time. So it'll be an evening in Europe and middle of the day in North America. But we'll keep you posted on that. So the first session will be a masterclass, so some state-of-the-art talks from around the world on the relationships between food and health, and then some up-to-date research talks on food structure, design, processing and digestion, food microbiome and health, and some of the future challenges and research opportunities. So the call for abstracts is effectively open now, but officially opens in a couple of weeks' time. So have a think about your abstracts. Registration will open at the same time. So we will have to charge a small registration fee. It looks like the maximum of that will be 100 Australian dollars. So not too much, but we will have some costs that we have to bear in terms of getting the information technology together. But we have until September to receive your abstracts, and then we can have the conference in November. As I say, a series of 4 sessions on consecutive days, 2 or 2.5 hour sessions, so that we can enjoy each other's company at the same time, hopefully around the world. So thank you for the opportunity to put that free advert up there, and I'll hand you back to Linda now to close or to tell you about the next session. Thank you so much.
Thank you very much. So I just really want to thank the chairs, both Mike Gidley from the University of Queensland and Alejandra Fani and Harjinder Singh from PAMI, from Ridet Institute PAMI in New Zealand. So thank you both for this. It was a great opportunity that you could join us live, and we want to thank all the speakers as well for joining us live. So I'm just going to hand you over to Andre, who's going to just give you a few announcements before session 5 begins.
Excellent. Thank you, Linda. And thanks again for all the speakers and the chairs. Hello to Australia and New Zealand. I think that worked pretty well. We should do that more often, I think. I agree with Mike. It worked well, and we should do the same probably at the second half of the year. So just, I have 2 more slides before we go on break. Here we go. I just would like to remind you of the INFOGEST network, and Didier gave a couple of slides yesterday. If you want to be part of it, and it's wide open to anyone really, just send an email to Nathalie Lamar, and you find her email on the website. Another easy way of communicating is LinkedIn, and I'm the administrator administrator for the LinkedIn group. So go to LinkedIn, type INFOGEST, and just follow it, or myself as well, follow myself. And if you have a paper to share or something, you can just share it and type @INFOGEST, not hashtag, but @INFOGEST, and automatically 750 people will be notified. Whether they read it or not is a different question, but it's an easy way of communicating. I would also like to remind you that we are live on YouTube. So if you go to the YouTube channel, In Vitro Food Digestion or INFOGEST, eventually find it. This is the QR code. We are live, and afterwards all talks will be uploaded. Uploaded onto YouTube, and I would like to thank all the speakers for agreeing to do so. We also on Twitter as a hashtag Virtual International Conference for Food Digestion. And then Linda mentioned the Menti poll, menti.com. There are 2 codes. The first one, from which country you are joining us from. That was yesterday's result. We have no means of knowing where you are joining us from because of GDPR issues. So we only have your email. So that would be a nice tool to see where you're joining us from. And this morning or this evening, we have quite a number of people from Australia, New Zealand, or from Asia. And the second one is topics for future INFOGEST webinars. So we have a monthly webinar, and again, we upload onto YouTube. Please add suggestions, 2 or 3 words maximum. There are fewer. Yes, by this morning there were 11 people had their say. So I can see food and drug interaction, peptide release, infant digestion, and absorption. So they are just pointers what you would like to see in the future. So that's all I have to say. The next session will start in 18 minutes at 9:25 Irish time. Bye, everyone. See you later.
So welcome back, everybody. So this is session 5, and it represents working group 3 in INFOGEST. So Muireann, if you can just share the share my PowerPoint, there you go. So it's just one slide, and it's just going to give you a summary of working group 3, which is all about the gut barrier and what food components and bioactives are permeable across that barrier. So what we did within working group 3 in INFOGEST is we split it up into subgroups, 7 subgroups, and I'm very lucky to have very accomplished scientists leading all of those subgroups. So in working group 3, the first subgroup is sample preparation and detoxification, and that is how you take food digesta and treat cell lines with it, or your models of the gut barrier with it. And Alina Kondrashina from H&H Global is leading that, and her email is just there on the screen. And then the next working group subgroup deals with the brush border enzyme activity. What are the enzymes, and how can we incorporate it into our digestion protocols, and how do we protect it in our cell barrier models? And that has been run by Gianfranco Mamon, who's in the Institute of Food Sciences in the National Research Council in Italy. The next one is allergy. What are good allergy models of the gut barrier? And that's run by Sean and Basten Net from WUR in the Netherlands. And the next subgroup is on permeability ring trial. And really this is all about, can we repeat all of our in vitro models? Can we repeat them across labs and use the same protocols? So Beatriz Morales from the Spanish National Research Council in Madrid, Spain runs that. And the next subgroup then is on gut barrier interaction with colonic fermentation. So this is devising protocols, taking colonic fermentation and putting it down on gut barriers. And that is our gut barrier models. And that has been run by Lydia Tomas from INA in Spain. And then the next subgroup is on cellular bioassays, which are all to do with what bioassays we have within our INFOGEST group looking at food bioactives, and can we standardize those protocols? And the contact for that is Elena Arnez in University College Cork in Ireland. And finally, but most importantly, how do our in vitro models of the gut barrier, how do they relate to real life? And that is in vivo models of nutrient bioavailability, and that has been led by Breg Graff from the Manchester Metropolitan University in the United Kingdom. So that is an overview of working group 3. So now let's begin our session 5. So if you can stop sharing there, Muireann, thanks a million. So on session 5, we have, I'm joined today by 2 of our working group 3 leaders, Lydia Tomas from INA in Spain. So give us a wave there, Lydia.
Hi, hello, good morning.
And then we also have Gianfranco Mamon, who's in, he heads up the protein chemistry group in the Institute of Food Sciences in the National Research Council in Avellino, Italy. So hi, Gianfranco.
Hi, everybody. Hi.
So Lydia, as a senior researcher, can you now lead invite our first speaker?
Well, thank you, Linda. See you later, Gianfranco. It's a pleasure to present and introduce you the first speaker of the 5th season, Héctor Tames. He's a PhD student at the Department of Microbiology and Biochemistry of Dairy Products of the Dairy Institute of IPLA, CSIC in Spain, and in a beautiful region as Asturias. I invite you to know the region. And he is to present his work about the development of an intestinal absorption model based on organoids obtained from pig duodenum tissue. So please, Héctor, go ahead.
Hello, everyone, and warm thanks to the organizers behind this event, and also for choosing my talk, entitled Development of an Intestinal Absorption Model based on organoids obtained from pig duodenum tissue. I am Héctor Tames, and I work at IPLA, the Dairy Research Institute, under the supervision of Lorena Ruiz and Patricia Ruas Mariedo. IPLA belongs to the Spanish National Research Council, or CSIC. And this is the biggest public research institution in Spain. It comprises 3 global research areas: society, life, and materia, and within life, 4 sub-areas, including food science and technology. This sub-area is composed of 8 centers around the Spanish territory. One of them is IPLA, where I work in one of the 7 integrating groups. The group I worked in is named Functionality and Ecology of Beneficial Microbes, or microhealth. We study the diversity and function of intestinal and food microbiota, and their roles in human physiology or pathology, or food characteristics. Our group has a collection of potential probiotics that we study from the functional, technological, and physiological perspectives to find the best application. The work I will present has been carried out in the framework of a national research project with the general objective of evaluating the role of bacterial exopolysaccharides from lactic acid bacteria or bifidobacteria in the bioavailability of bioactives in dairy matrices. The interest in these polymers is based on their interesting technological applications already exploited, like modifiers of food microstructure, permeability, or viscosity. However, the influence of bacterial EPS on absorption of nutrients or bioactives hasn't been fully studied. Then, the working hypothesis is that the presence of EPS synthesized by lactic acid bacteria or bifidobacteria during milk fermentations could affect the bioavailability at intestinal level of bioactive compounds in the fermented product. To address this hypothesis, the working plan includes the selection of 2 bioactives and 2 in vitro intestinal models. To then be able to compare results and optimize the system that most resembles in vivo situation. After that, we will try to propose one model for studying intestinal bioavailability of bacterial bioactives by evaluating bioaccessibility, intestinal absorption, and biological activity in animal models. Starting with the bioactives study, we have chosen the gamma-aminobutyric acid, or GABA, based on its importance as the main inhibitory neurotransmitter in the nervous system of mammals. Most of this molecule is intrinsically produced from glutamate. But microorganisms in the gastrointestinal tract can produce it too, opening a new area of knowledge studying interactions between digestive and nervous system, also known as the microbiota gut-brain axis. The microorganism to study as a source of microbial GABA will be Bifidobacterium adolescentis, bacterial species with status of qualified presumption of safety by EFSA, thus allowing their use for humans and animals. The other bioactive compound chosen is riboflavin or vitamin B2, substrate for flavin mononucleotide and flavin adenine dinucleotide synthesis, important redox cofactor. As we are unable to produce riboflavin, most of this vitamin comes from diet, but also microorganisms in the intestine or in foods can produce this molecule through the synthesis route shown here. The bacteria used as a source of microbial riboflavin will be Bifidobacterium longum subspecies infantis, which is commonly present in breast milk and baby's intestine, but also in infant formulas, stimulating correct growth in early stages of life. Now, regarding cellular models that we are studying, it must be pointed the differences between the large and the small intestine, where absorption processes mainly take place, whilst in the colon is a place where microbial fermentations occur. There are many available cell culture lines, SCACO2 or HT29, for example, but the majority of them come from colon adenocarcinomas. They are composed of only or mainly one cell type from the multitude of them integrating the intestine. This model can be useful to study individual contribution of cell types, but has some limitations in the study of intestinal function. To overcome these drawbacks, we will use organoid-based models. Organoids are three-dimensional multicellular in vitro tissue constructs that mimic its corresponding in vivo organ, They can be used to study aspects of the original organ in a culture dish. They can keep organ architecture and cell types and grow under specific culture conditions for some time, being proposed as a tool for personalized medicine. Organoids can be cultured in vitro from a single adult stem cell coming from intestinal crypts that can generate all the other cellular types. The culture is supported by a three-dimensional matrix resembling in vivo tissue structure, commonly commercial material. So, the global purpose of my work will be to study intestinal absorption of two different molecules in two different cellular models. Depending on chosen compound and cell types, the transporters involved or mechanisms can differ. Then we will choose the best experimental design to follow our work in the framework of the project. To address this, I will present preliminary results of these three specific objectives. First, to set conditions to obtain a differentiated in vitro intestinal model of absorption of nutrients using commercial cell lines. Second, to establish a three-dimensional epithelial cell culture based on healthy pig intestinal cells to obtain organoids that can be transformed to a two-dimensional monolayer. And finally, to compare standard model based on cell lines and new proposed model based on organoids. Starting with the first of them, we mixed two different cell lines composed mainly of one specific cell type. CACO2 cells, which contain enterocytes, the absorptive cells, and HT29-MTX cells, developed adapting HT29 cell line to methotrexate. This has both enterocytes and goblet cells, which are capable of producing mucus. These two cell lines were seeded onto cell culture inserts with a porous membrane, allowing cell attachment and growth. Afterwards, we checked the flow of substances between the two compartments, apical one, resembling luminal space, and basolateral. Here, you can see an image of culture cells stained with DAPI for nucleus, fluorescent green antibody for CO1 tight junctions, fluorescent phalloidin to visualize the cytoskeleton, and CI5 fluorochrome for cell membrane. To evaluate the strength of junctions between the cells, we used transepithelial electrical resistance measurement, or TER, whether in the form of single measurements at different time points with millicell, or continuous measurement using cell scope in culture conditions, which also allows to monitor capacitance, a magnitude inversely related to system impedance. To follow up cell layer permeability, we use Lucifer yellow as a reporter signal of paracellular trafficking. This molecule can be measured at both sides of the membrane using fluorimetric measurement. We followed the evolution of both TER and Lucifer yellow permeability, calculated as a ratio between the apical and total amount of the molecule in the system, in three different CACO2 to HT29-NTX ratios for 24 days in culture, including medium changes every 2 or 3 days. Resistance values, lines, never stopped increasing, reaching values over 500 ohms, whilst Lucifer yellow permeability, bars, stabilizes around the 3rd week in culture. With this data, we have selected to standardize conditions the ratio of 70 to 30 CACO2 versus HT29 MTX cells and carry out experiments around the 21st day after seeding. Using continuous monitoring, the results were comparable to static measurements, with electrical resistance or impedance as an inverse of capacitance, clearly increasing from the 5th day in culture, as we have highlighted here. With previous conditions, we have carried out experiments to evaluate absorption of GABA and riboflavin with the same experimental design in both cases. Cells were seated onto a porous membrane inserts and allowed to differentiate. After that, the bioactive compounds were applied in the apical site, and their transit between compartments monitored at 3 and 6 hours after addition. After these time periods, aliquots from both compartments were analyzed via HPLC, showing absorption of both substances. For GABA, absorption rates represent 2 and 4% of the total amount for 3 and 6 hours. In the case of riboflavin, that represents 1 and 2% at the same time points. Next, we tried to develop the new model based on three-dimensional cultures of pig intestinal cells, and to do so, small fragments of pig intestinal tissue from duodenum were collected at the slaughterhouse. After controlled degradation of extracellular matrix, small crypt fragments were released and allowed to grow in appropriate 3D matrix and medium. Stem cells were previously identified after a complete degradation of other fragments releasing individual cells, some of which express a stem cell marker, LGR5. Around 1% of the cells were positive for this marker using flow cytometry. Once in culture, crypt fragments grew and form a closed structure with microscopic morphological features of intestine, such as crypts and domes. Tight junctions between the cells were also observed using confocal microscopy, as shown here. Once we obtained sufficient number of organoids, 3D structures were disrupted mechanically and enzymatically using trypsin to form a two-dimensional monolayer of cells, which seated onto a porous membrane covered with matrigel allowed us to carry out absorption experiments. In this case, we started evaluating the cell's absorption of monosodium glutamate, salt of glutamic acid, which after a decarboxylation yields GABA. Monosodium glutamate is commonly ingested with different foods, so dietary source of this compound is important. After HPLC measurements, we have observed that around 8 and 13% of the salt have crossed the membrane at 3 and 6 hours respectively. At the present time, we continue evaluating both models with mentioned substances, once that experimental designs were set up. We are working with different amounts of bioactive compounds at defined absorption time of 3 hours to contrast the behavior of the cell systems. In the future, our steps will be focused on integrating the chosen cellular models and bioactive compounds from bacterial origin with food matrices and exopolysaccharides. In this regard, we will also include a previous step of in vitro static digestion developed in the context of INFOGEST action to evaluate the influence of these polymers in bioactive absorption. Finally, I would like to thank to all the people involved in this work. All the experiments were carried out at IPLA, at the microhealth group, with funding from regional and national agencies, and also support from several collaborators. Thank you so much for your attention. Please pose your questions.
Thank you, Hector. Please, if you can turn on your camera and and turn your microphone. Thank you. I'm going to read some questions for you. So, okay, question is from Sebastian Mers. How do you get your reactive compounds inside the organoids?
Okay. it's the same experimental design as explained for the cell line co-culture. We seeded the organoids onto a porous membrane. In this case, working with organoids, it needs matrigel to form the matrix to the cell attachment, and evaluating the amount of compound in both compartments, apical and basolateral. It's the exact experimental design.
Okay, so I don't know, but maybe we're continuing with the question, because you cannot make sure that the bioactive is not to be attached around the sphere of the organoid. I think
okay.
could, because okay, sorry, continue.
I went too fast because I didn't explain too much about when I'm working with 3D organoids and 2D organoids. I mean, we are only in a three-dimensional state for culturing and growing and all these things. But for experiments, we need a two-dimensional layer. So we disrupt that 3D organoids to build up a two-dimensional layer upon the matrigel matrix in the insert. I'm not sure if it's clear now or...
You mixed both techniques about the insert and the organoid. Okay, thank you. You have another question from Gianluca Picarello. Thank you for your clear presentation. Did you check if 2D organoids express brush border membrane peptidase?
Not yet. The ongoing work deals with that kind of experiments. We are now trying to assess what kind of cells are there in the organoids. Are they expressing mature cell markers to consider an active cell? And no, we didn't assess it yet, but we are doing now this kind of experiments.
Okay,
thank you.
Thank you. I think that we don't have too much time for another question, so we go ahead. Thank you, Hector. It's a very interesting, very good, innovative model. It's very impressive. So please, Gianfranco, if you can, please introduce the next speaker.
Okay, thank you, Lydia. I would like to introduce the next speaker of this section, Leah Fleury. Leah is a PhD student at INRA Institute from France, and she will talk about comparison of food proteins from diverse origins of DPP4 inhibitor activity in vivo rat plasma and in vitro after intestinal barrier passage. So I hand over to Leah.
Good morning, everyone. So before starting, I would thank the organizing committee for allowing me to participate in this event. I'm a student PhD from Lille University, and today I'm going to present to you my work on the in vivo and in vitro comparison on the DPP4 inhibitory potential of food proteins from different sources after gastro-intestinal digestions. Let me start this presentation with a quick part of context. Currently, the world faces a rising demand for protein, explained by a worldwide increase of inhabitants and a general improvement in the living standard. This leads in a shortage of the protein resource and to many environmental problems. At the same time, the world population is getting fat. 650 million people are obese, and this pathology is often associated with metabolic disease which degrades health condition. In this context, there is an interest in having a reasoned use of proteins and a need for a better characterization of them. This characterization can be done by studying the role in the mechanisms associated with energy homeostasis, because it had been shown that high-protein diets improve glucose homeostasis in rodent and human, healthy and diabetic people. This improvement of glucose homeostasis could be explained by the protein and amino acid effect on the stimulation of insulin and incretin hormone secretion. Furthermore, recent studies shows an effect of food proteins on the inhibition of DPP4 enzyme, which is involved in the glucose regulation. GLP-1 and GIP are two incretin hormones secreted by intestinal cells in response to food intake. These two hormones lead to the reduction of blood glucose after a meal, and the DPP-4 enzyme inactivates them and therefore interferes with the blood glucose regulation. As I said in the previous slide, some peptides from food proteins are excellent natural inhibitors of DPP-4 activity, and so there is a growing interest in employing them for the prevention of type 2 diabetes and obesity. Therefore, the goal of these studies is to compare and characterize several proteins from different origins and their DPP-4 inhibitory activity, and in a second time, to develop an in vitro model of intestinal digestion and absorption for study bioactive peptides from food protein digestion and DPP-4 activity. To carry out this model, an in vivo study was done to have a base of results to compare. During this in vivo protocol, 5 different protein sources on a water solution were tested on male star rats to measure the effect of protein on DPP-4 activity 30 minutes after ingestions. Thus, 30 minutes after rats were first feeding with proteins, blood samples were collected and the DPP-4 activity was measured thanks to the addition of a substrate which fluoresces during its cleavage by the enzyme naturally present in the plasma of rats. The results of this experiment are presented as a percentage of DPP-4 inhibition calculated in relation to the control group. It can be observed that all proteins except casein inhibit DPP-4 activity and pea protein lead to the best enzyme inhibition. This experiment was done to compare results to the in vitro experiment, which could lead to similar results. This slide presents the workflow of the in vitro experiments. Same proteins as the in vivo experiment were digested in vitro with the INFOGEST protocol, which has been adapted for protein digestion only. Gluten and whey proteins were added compared to the in vivo protocol, and blank digestion was used as a control. This digestion was done with the salt and peptidase without protein. Then, intestinal samples have been put in contact with the brush border peptidase present on the co-culture of CACUT2 HT29-MTX cells to complete the digestion. After contact, DPP-4 activity was measured at basal site after absorption by the intestinal cells. And to complete this experimentation, peptides from apical and basal sites were analyzed by mass spectrometry, and an in silico analysis of the DPP-4 activity was made. Before beginning experimentation on DPP-4 activity, I've studied the effect of proteins on the intestinal barrier. To do that, I measured in first part the transepithelial electrical resistance, TER, before and after contact with proteins, and in a second part, the cell permeability with a lucifer yellow test. These tests are strong indicators of cellular barrier integrity and cell permeability. First of all, it's important to specify that protein digests were not cytotoxic in this condition, and there is no multilayer in insert. The graph at left shows the protein effect on transepithelial resistance expressed in ohm, and the graph at right shows the permeability expressed in centimeters per second. We can observe from this graph that hemoglobin, casein, and whey intestinal samples decrease the TER after treatment, and only hemoglobin digests decrease cell permeability to an acceptable extent. We can conclude from this slide that digested proteins affect differently the intestinal barrier integrity. To go further in the understanding mechanism, I made a contact of 24 hours between the intestinal digestion samples and the co-culture cell to measure the protein effect on the expression of genes involved in intestinal barrier integrity. I've chosen to study the zonular occludins, occludin, and claudin 1 and 4 genes, which participate to the synthesis of tight junction proteins and paracellular seal. On this graph, results are expressed in mode of control, and it can be observed that the intestinal protein digest induces a significant decrease of the gene expression, which can partially explain the previous results. We can conclude from this slide that the arrangement of cell, the non-cytotoxicity of protein digest, and the effect of protein on the expression of gene involved in the traduction of tight junction proteins could impact the peptide passage. Before analyzing the DPP-4 activity of basolateral side, I tested the effect of intestinal samples on the DPP-4 gene expression at 24 hours on a co-culture cell. So, results on this graph are expressed in form of DMM control, and we can see that all the protein digest significantly inhibit the DPP-4 gene expression except digest from milk protein. This result corroborates quite well the in vivo results. So after, I measured the DPP-4 activity after passage of the intestinal barrier. To measure the basolateral DPP-4 activity, I've done a fluorescent kinetic with the fluorescent substrate, a human recombinant DPP-4 enzyme, and basolateral samples taken after 1 hour 30 minutes of contact between protein digest and co-culture cells cultivated on insert. As you can see on this graph, results are expressed as a percentage of DPP-4 inhibition relative to the blank digestion to compare with the in vivo experiment. We can observe that only digest of hemoglobin, casein, ovalbumin, and whey inhibit DPP-4. That means there are some peptides on basolateral side which inhibit DPP-4 activity. To go further, I analyzed apical and basolateral peptides by mass spectrometry. To carry out the study by mass spectrometry, I took samples at the apical and basal site of the insert after the contact with protein digest and co-culture cells. These samples have been dried and resolubilized in water with 0.1% TFA. By LC-MS analysis, we obtain a peptidic map, as you can see here, which represents all the detected ions present in one sample and potentially peptides, according to the retention time on the C18 chromatography, their mass to charge ratio, and their intensities. It's the shade of gray. This map was performed for each protein at the two sides to compare or identify peptides. So, after making all the peptidic maps, the software Progenesis QI is able to compare them to perform a principal component analysis. In ACP, the cloud of points represents all the detected or identified ions in the map. Samples are positioned on the ACP according to the peptides which compose them. The further apart samples are, the more different they are in terms of peptides population and vice versa. On the first graph, we can see that peptides are significantly different between the apical and basal side, and on the two other ACP, each color is associated with a protein, and we can see that peptides are significantly different depending on their origin in the two sides. Then I identified each point and saw each peptide in terms of amino acid sequences with PIC software. In this representation, I choose to show as an example the subunit alpha of hemoglobin. On this schema, we can see the amino acid sequence of the subunit alpha in black, and each blue line represents an identified peptide located on the protein sequence. It's possible to visualize different zones of a protein resistant to the hydrolyse. Furthermore, there are peptides found in both sides which are resistant to the digestions. The proportion of these peptides are different according to the protein. On these Venn diagrams, it's represented the number of peptides generated at the apical pole in black, at the basal pole in orange, and the number of peptides in common in gray. We can conclude from this Venn diagram that many peptides cross the intestinal barrier, and some new peptides are generated by the intestinal passage. Thanks to the identification of peptides by mass spectrometry, I was able to assign a predicted IC50 to each of these peptides thanks to a QSAR analysis. During this in silico analysis, I chose to take into consideration the Z-scale only. In this first table, I calculated the percentage of bioactive peptides with an IC50 for the DPP-4 activity minor to 500 micromolar produced per protein during digestions. De novo peptides were included in this analysis. After, on the two other graphs, I represented a classification of the inhibitor peptides of each protein by IC50. Regarding the results, I focused on the basal level analysis. When we look at the percentage of DPP-4 inhibitor peptides per protein, we realized that it's whey proteins first and then vegetable proteins that tend to create the most inhibitory peptides after absorption. And it's casein which produces the fewest and the least potent DPP-4 inhibitor peptides in proportion. These observations are in line with the trend observed in the in vivo experiment, 4P in particular. However, these results should be taken with precaution because all these representations allow a qualitative analysis. Indeed, the exact quantity of each peptide is not integrated in this analysis. Another point is important to underline. Peptides of less than 4 amino acids are not identified because of the current limitations of mass spectrometry methods. So, we can just conclude that all the digested proteins generate peptides with high inhibitory potential, but some proteins produce more DPP-4 inhibitor peptides variety than others. After a synthesis of all the results regarding to the effect of protein digestions on the DPP-4 activity, we can say that the digestion of some proteins affect intestinal barrier by modulating the expression of genes involved in the barrier integrity, which could promote the passage of some peptides. Protein digest differently inhibit DPP-4 activity. Some peptides from protein digestion cross the intestinal barrier, and many others are generated by the brush-border peptidase during the passage. All proteins generate potential different DPP-4 inhibitory peptides, and on the basis of all the results, vegetable protein and hemoglobin seems to be the best candidate to inhibit DPP-4 activity. Now, when we are interested in the comparison of the in vitro model with the results of the in vivo experiment, we can say that there are no trends found between the in vivo results and those testing DPP-4 activity after passage, despite a similar tendency of QSAR and gene expression results compared to the in vivo results. My hypotheses are that models are maybe too much different, rat in vivo protocol versus human in vitro digestions. The time of digestions are different too, 30 minutes in vivo versus complete digestions in vitro, or peptides from pea and gelatin cross the intestinal barrier in too small quantity in the limit of detection. My perspectives are to sampling more later, 1 or 2 hours in the in vivo protocol, and try to concentrate basal sample before testing DPP-4 activity in the in vitro model. I can conclude that these results allow to better characterize and compare the health potential of proteins regarding their bioactivity after gastrointestinal digestions. To finish, I would like to thank the organization committee, my thesis supervisors, and all the people who helped me to carry out these experiences. Thank you for your attention.
Okay, thank you, Lea. Excellent. That's very nice, very interesting. Thank you for your presentation. And we have some questions. I try to read some of them. Okay, the first is from Pasquale Ferranti. Do you know if the DPP-4 inhibitors from the food proteins may have an impact also on the gut microbiota?
Hello. So it's possible that peptides from food proteins can inhibit the peptides, the peptidase on lactobacillus cell, bacteria, if they can reach the colon. But I don't test it, so I think it's possible.
Okay. And a question from myself is a technical question about the simple preparation for in vitro experiment. Did you purify samples before the passage to the cacotube cells?
So no, my samples are not purified, just I heated them after the digestions and just centrifuge it. That's it.
Okay, and again, another technical question about if you have diluted the digested proteins after INFOGEST digestion before contact with the cell, and if so, how did you choose the dilution?
So I've no dilute my intestinal sample for the passage on the cell, but I've done a dilution for the RT of the qPCR test. Just I diluted to 5 microgram by ml with DMM.
Okay, another question from Gianluca Picariello. He supposed that possible peptides in plasma undergo breakdown or clearance in time. Does the DPP4 inhibitor activity in rat plasma change in time? Did you try to identify by LCMS food-derived peptides in rat plasma?
I try to identify some peptides. No, I don't try to do that. It's I would to be for later experience, but actually I don't do that now. And no, sorry.
Okay, thank you again, and we might move to the next speaker. I ask to Linda to introduce him.
Thank you very much, Gianfranco. So our last speaker, it gives me great pleasure to introduce Marta Santos Hernandez. She is a final year PhD student at the Spanish National Research Council, the CSIC in Madrid. So Marta's talk is food protein digests as inducers of CCK and GLP-1 secretion in STC1 cells. So if you can play her video.
Good morning. First of all, I would like to thank the organizers for giving me the opportunity to present my results about food protein digests as inducers of CCK and GLP-1 secretion in STC1 cells and the receptors involved in enteroendocrine cell signaling. Gut is considered the largest endocrine organ due to the number of endocrine cells and also the variety of hormones produced. The intestinal epithelium is composed by enterocytes, goblet, tuft, pained, and enteroendocrine cells. Some of the last cells can act as sensor of the luminal content, and as a response, they secrete anorexigenic hormones like cholecystokinin, CCK, and glucagon-like peptide 1, GLP-1, that are involved in regulation of food intake and gastric emptying, and GLP-1 is also implicated in the regulation of glucose homeostasis. Proteins are the macronutrient with greater satiating effect compared to an isoenergetic intake of fats and carbohydrates. However, little is known about the structural characteristics required of protein-derived digestion products and the euprotein-coupled receptors involved in the signaling. For instance, calcium sensing receptor or GPRNT3 are highly expressed in human and mouse gastrointestinal tract and also in the mouse enteroendocrine cell line STC1. The main objective of this work was to evaluate milk and egg white gastrointestinal digests and peptides thereof as inducers of CCK and GLP-1 in the enteroendocrine cell line STC1 and the receptors involved in peptide signaling. The main objective will be divided into 3 partial objectives that I will mention through the presentation. For the first partial objective, human genome samples of casein and whey protein were obtained in collaboration with AgroParisTech, and in vitro digests of the same substrates were prepared following the INFOGEST protocol. The digests were characterized regarding protein, peptides, and amino acid content, and were tested in STC1 cells. The results for CCK release show an increase for all digest, gastric digest, and intestinal digest, although the response was maximized with intestinal digest of both substrates. We established a comparison between in vitro intestinal digests and human jejunum samples, where we can observe the similarity in CCK secretion between human jejunal digests and in vitro digests for casein and whey protein. Similar results were obtained in ELP1 release with whey protein in vitro digest and human jejunum samples. However, human jejunum samples of casein show higher ELP1 secretion than the in vitro intestinal digest, probably due to a higher degradation of in vitro digests or the existence of specific peptides found in human jejunum samples. Gene expression of CCK and proglucagon showed similar results between in vitro and human samples of whey protein. However, there were some differences in casein due to the inter-individual variability. With all these results, we can conclude that STC1 cell line is a good model to measure hormonal secretion in presence of gastrointestinal digests, and also the simulated gastrointestinal protocol was validated. We have also seen that the hormone secretion could be affected by the degree of hydrolysis, so we decided to evaluate the influence of peptide size in CCK and ELP1 release with egg-white gastrointestinal digests. Egg-white were digested and the nitrogen distribution content was evaluated. At the end of the gastric phase, 7% of the total nitrogen content was in the insoluble part. Less than 1% was found as free amino acids, and 92% corresponded to proteins and peptides. At the end of the intestinal phase, 28% of the total nitrogen content corresponded to free amino acids in the soluble part, whereas 71% was in form of peptides and proteins resistant to pancreatic enzymes. The intestinal digest was fractionated by size exclusion chromatography in 3 fractions. The first one, composed by proteins and peptides with a molecular weight higher than 3 kilodaltons. The second one, that contained peptides with a molecular weight between 3 and 0.5 kilodaltons, and the third fraction that corresponded to peptides lower than 0.5 kilodaltons and free amino acids. Egg-white digests and second intestinal fraction were tested in STC1 cells, and the results were quite revealing. Fractions containing peptides with a molecular weight higher than 0.5 kilodaltons induced ELP1 response, whereas short peptides or free amino acids did not show any differences in comparison with the control. For that reason, peptides longer than 0.5 kilodaltons act as main inducers of ELP1 secretion. By contrast, CCK release was induced by peptides and, in a lesser extent, by free amino acids. Because peptides seems to be the main inducers of these hormones, milk and egg-white peptides were evaluated as inducers of CCK and ELP1 secretion, and as well as the receptors involved in the peptide signaling. Peptides identified from milk and egg-white digests were synthesized, selecting peptides with different sequence length, hydrophobicity, and isoelectric point. Because peptide sequence was found to be crucial for hormonal secretion in the initial screening of the peptides, a structural modification of those with secretagogue effect were performed. In addition, we evaluated the effect of peptides in cells pre-treated with specific inhibitors of the calcium sensing receptor and GPR93. These graphs show the hormonal secretion induced by the peptides found in human digest, displayed in bold, and the structural modifications, and the modified sequences. We can observe that the loss of sharing at the amino terminal region of the peptide kappa casein 33-37 reduce CCK and ELP1 secretion, highlighting the relevance of this amino acid residue. Peptide alpha S1 casein 96 found in human digest had a notable effect on CCK and ELP1 secretion levels, but this effect was increased with the derived tetrapeptides 90-93. In the case of egg-white derived peptides, the removal of tryptophan from N-terminal end of the lysozyme fragment 123-129 decreased CCK and ELP1 secretion, demonstrating that the amino acidic sequence is crucial on the induction of CCK and ELP1 release, and also the relevance of the amino acid tryptophan. To evaluate the influence of calcium sensing receptor and GPR93, cells were pre-treated with antagonists of these receptors. The secretory effect of kappa casein fragment 33-37 on CCK and ELP1 decreased in presence of both antagonists, demonstrating their involvement in the activity of these peptides. These two receptors are also involved in the signaling of alpha S1 casein peptide 90-96 for CCK secretion and lysozyme 109-119 for ELP1 secretion. With all these results, we can conclude that CCK and ELP1 secretion and gene expression in the enteroendocrine STC1 cell line are induced by simulated gastrointestinal digests of casein and whey protein in a similar way than those found with human jejunal digests for both substrate, validating the cellular model used and the representativeness of the digests. We can conclude also that the peptide fraction released during gastrointestinal digestion of egg white is the main inducer on CCK secretion in STC1 cells. However, ELP1 secretion is mainly induced by peptides with a molecular weight higher than 500 Dalton released during gastrointestinal digestion. The amino acidic sequence is crucial on the induction of CCK and ELP1. For instance, the loss of the amino terminal amino acid of peptides kappa casein 33-37 and lysozyme 123-129 produces a reduction on the secretory effect for both hormones. And finally, the secretory effect of peptides kappa casein 33-37, alpha S1 casein fragment 90-96 and lysozyme peptide 109-119 on CCK and ELP1 decreases in the presence of calcium sensing receptor and GPR93 antagonists, demonstrating their involvement in the activity. And thank you so much for your attention.
So thank you very much, Marta. That's a lovely talk. So we've quite a few questions come in, but I want to ask you first, with the number of peptides that are out there now that we know induce GLP-1 and CCK, can you predict now what it needs in a sequence to be an inducer?
Well, we are trying to know that, but we don't know yet. We know that, for example, for ELP1, it's some peptides with high hydrophobicity and high isolatory point. but they are not characteristics strictly required for the GLP-1 secretion. It's the sequence, the most important, and we cannot determine what is the structural characteristic required for that.
Okay. So from Shauna Bastian-Net, she asks you, before the STC1 stimulation, did you inactivate the digestive?
Yes, we inactivate the pepsin and the gastric digestion to pH 7. And then the intestinal digest, we inactivate the enzymes by heating, because we thought that is better than the use of a cocktail, inhibitor cocktail of enzymes, because can be affected to the pathways to the hormonal secretion.
Yeah, yeah. And another question, was the effect of the bile salts and enzymes taken along as a negative control, and did they induce CCK and GLP-1?
Well, now we use the control, the buffer in the which samples are diluted. We did a blank of enzymes and tested in GLP-1 secretion, and we didn't see any differences in comparison with the control. So in that case, the blank of enzymes, so the enzymes don't affect in the GLP-1 secretion.
Okay. And another technical question is, why did you select a 24-hour treatment to study gene expression when you know that it's regulated after 2 to 4 hours?
Well, I'm not sure if that question is for me, because the gene expression I measure in the 2 hours, in 2 hours, it is the same gene expression that for secretion, so it's the same time. We are thinking about measuring in different time points, because it's not the same to measure secretion than gene expression. But the results I showed, that's for 2 hours incubation.
Okay, so another question from Patricia was, how easy is it to handle the STC1 cell line?
Yeah, well, it's easy to handle, so, but you have to be cautious with different contaminations. And the problem of the STC1 cell is that it's heterogeneous. So for that kind of assay, I usually use the cells between passages 15 to 35. To 35, because we saw that it's in that in that range of passages that the hormones secretion could be accuracy, and we can reproduce the similar results.
Excellent. And I think it's very interesting, Marta, that as food is digested, it has the ability to induce these satiety hormones, and then it often loses those abilities by the time it gets to the intestinal phase, certainly with casein, but then improves it with other foods. So I think it's really interesting to look at what happens during gut transit. So thank you very much, Marta. And I think that this is the end of our session 5. So I'd like to thank Lydia, if she'd like to come on the camera, and also Jan Franco for being chairs of this session. So Andre, do you have any comments to make before we close session 5? No, he's just given me the thumbs up. So we're going to close session 5, and then session 6 will begin at 10:45 Irish time. I know it's different times everywhere else. And it's going to focus on digestive amylases and starch digestion. So see you then. Bye-bye.
So welcome back. We have 2 more minutes until the start of the next session, and I would like to introduce the working group leaders of the next working group 5. And we have Carolina Orfila and Nadia Siegert here. If you can show yourself, here we go. And I hand over to you. But before, I would like to thank the previous speakers, not just the chairs, but also the previous speakers. There were really good talks. We didn't have time to answer all questions, and just a reminder that any unanswered questions will be answered by email after the conference. Okay, and when you write a question into the question and answer box, please refer to the speaker, because that's much easier to us than to identify which question is for whom. Okay, Nadia, there you go.
Thank you very much. And yeah, welcome everybody. It's my pleasure to introduce you to our next session, number 6, on amylases and starch digestion. My name is Nadia Siegert from Fresenius Kabi, and I'm co-chairing this session with Caroline Orfila from the University of Leeds. And we are the co-leads of the work group 5, together with Bin Zhang from South China Institute of Technology. And our work group aims to provide a forum to discuss amylase and starch digestion topics, to harmonize also the method to measure amylase activity of commercial enzymes, and to propose a robust and reproducible method for simulating starch digestion. We also have a regular seminar, the next one coming up next month, and it will be given by Dr. Eduardo Capuano from the University of Wageningen. And so please have a look to the social media channels that we have. And with that, I hand over to Caroline, if you could show yourself.
Thank you very much, Nadia. Yes, so focusing on today's conference, we have 3 speakers from the Quadram Institute in Norwich in the UK. We must point out that we did select speakers from other places as well, but due to time zones, they have presented either last night or this morning. So helpfully, Starch has managed to infiltrate the rest of the conference, which is very nice. But our Quadram speakers have very diverse topics and perspectives, and we're really looking forward to all 3 of them. Our first presentation is by Trey Kuev, on the structural changes and physiological responsiveness of starch hydrogels in the human gastrointestinal tract. So let's listen to his presentation together. Thank you.
Hello everyone, my name is Trey and I'm a final year PhD student at the Quadram Institute and at the School of Pharmacy at UEA over at the Norwich Research Park. A great deal of my PhD project was dedicated to exploring the viability of starch hydrogels as orally administrable targeted colonic drug delivery systems, predominantly by means of advanced NMR spectroscopy techniques under solution, solid state, and HR mass conditions. According to the British Pharmacopoeia, solid and gel-type pharmaceutical excipients are subjected to 2 main methods of quality control: disintegration and dissolution testing, where these probe excipients' ability to break down into small enough particles and to dissolve into the media, facilitating absorption and metabolism in the upper gastrointestinal tract. However, one shortcoming of these simulation techniques is that they more often than not focus on one stage of the human gastrointestinal tract, usually either the gastric or the small intestinal stage, and usually only mimic the pH conditions. In this way, they often fail to account for physiologically relevant gastrointestinal components, such as hydrolytic enzymes. This can result in an over-exaggeration of excipients' ability to retain structural integrity across the gastrointestinal tract, which in turn overestimates their ability to deliver the active pharmaceutical ingredient in the physiologically relevant concentration to the target site. In order to gain a functional understanding of starch hydrogels across the gastrointestinal tract, we focused on 2 starch varieties: a lower amylose normal maize starch and a high amylose hylon 7 maize starch variety. In order to simulate the entire length of the human gastrointestinal tract, we loaded our starch hydrogels with 3 different drug molecules and subjected the drug-loaded hydrogels to the INFOGEST protocol of in vitro digestion, featuring an oral, a gastric, and a small intestinal stage, followed by in vitro colonic fermentation over the course of 72 hours, sampling both the starch hydrogel matrix itself and the digestion and fermentation media at predetermined time points. What we wanted to know was what structure-function links govern the behavior of starch hydrogels across the entire length of the human gastrointestinal tract, what the effect of these excipients was on the colonic microflora, and whether we could exploit these structure-function links to fine-tune the pharmacokinetic profile of the small drug molecules in the large intestine. One of the first things we wanted to know was how much of the actual starch hydrogel matrix was being digested by the end stage of the small intestine, by which point the substrates would have been exposed to both salivary and pancreatic alpha amylases, and how that translated to the bulk structural integrity of the starch hydrogel matrix. What we found was that the lower amylose-containing gel was more than twofold more digestible in the upper gastrointestinal tract compared to the high amylose variety. And this increased susceptibility to amylolytic degradation resulted in a faster loss of structural integrity as the gels traversed the simulated gastrointestinal tract. We then focused on what molecular structural parameter changes were taking place, which resulted in the change in bulk structural behavior we had observed. What we saw was that as gels traversed the gastrointestinal tract, there was a progressive decrease in the amylopectin fraction, which was more emphasized in the low amylose starch variety. What we also saw was that there was a decrease in the proportion of longer chains in the hydrogel organization, accompanied by an increase in shorter chains. Across the entire length of the human gastrointestinal tract, starch is subjected to the cumulative action of alpha-1,4 specific enzymes of mammalian or host origin and ones of commensal bacterial origin featuring both alpha-1,4 and alpha-1,6 specificity. In order to gain a further understanding into the change in molecular structural parameters we observed, we wanted to know whether there were observable changes in the degree of branching in our starch matrices across the gastrointestinal tract, and how these change under the influence of mammalian and bacterial enzymes. As expected, what we saw was that in the upper gastrointestinal tract, there was a preferential cleavage of alpha-1,4 linkages, whereas in the lower gastrointestinal tract, there was a pronounced drop in the total degree of branching, likely to result from preferential cleavage of alpha-1,6 linkages. So far we knew that there was an increase in the total proportion of short chains in our starch gels, and this was accompanied by changes in the degree of branching of the hydrogel matrices as they traverse the human gastrointestinal tract. But what did that mean in terms of molecular structural mobility? We probed the local molecular structural dynamics in our starch hydrogels across the gastrointestinal tract, and what we saw was that there was an increase in the degree of local mobility of starch chains existing within the starch hydrogel network. This was occurring hand in hand with the previously observed loss of structural integrity. Cumulatively, these data point towards the increase in motional freedom of starch chains within the hydrogel matrix, as the overall bulk matrix was being degraded by the amylolytic enzymes. When we investigated the solid-state spectra of the starch hydrogels at the end of the INFOGEST digestion stage, we observed the presence of new peaks, which were arising from species existing exclusively in the solvent phase of the starch hydrogel network. These peaks had the exact same chemical shift as species in the digestion media and also disappeared in the initial stages of fermentation. When we compared the chemical shift of these peaks with ones arising from equimolar mixture of reducing sugars, we concluded these newly observed peaks were arising from products of digestion being trapped within the water phase of the starch hydrogels, which were preferentially being utilized as carbon sources by commensal bacteria during the initial stages of fermentation. These data were further confirmed by the metabolites present in the fermentation media, where we saw a sharp drop in the concentration of glucose and maltose during the first 6 hours of fermentation. Okay, so far we had a pretty good idea of the structural changes starch hydrogels were undergoing on both bulk and molecular level. But we hadn't answered arguably the most important question when investigating starch hydrogels' viability as colonic drug delivery platforms, namely, what the pharmacokinetic profile of the loaded small molecules was from the starch excipients. What we observed was that there was a minimal to no release of the small molecules across the upper gastrointestinal tract, where the drug release was confined exclusively to the large intestine. What we observed were much slower release kinetic curves compared to most currently utilized colonic delivery systems, which follow a more sigmoidal type release profile. What is more, the release mechanism appeared to be matrix degradation dominated, as evidenced by the simultaneous drop in matrix integrity. One aspect of the pharmacokinetic profiles we observed and we were curious about was the differential release we noticed for the 3 different drug molecules. This could be explained by the different degree of interaction between the drug molecules in the matrix, which mimic the release kinetics order. One of the auxiliary aspects of exploiting the ability of starch hydrogels to escape upper gastrointestinal digestion and be degraded in the large intestine by the cumulative action of commensal bacterial amylolytic enzymes is the production of health-promoting bacterial metabolites such as short-chain fatty acids. And indeed, our drug delivery matrices were fermented in the large intestine, which led to the production of gas and short-chain fatty acids. One aspect of delivering physiologically relevant drugs to the large intestine that is often neglected in the context of pharmaceutics is the impact of the therapeutic agent on the gut microbiota. What we wanted to know essentially was whether the presence of the small drug molecules was in any way leading to perturbations of the commensal bacterial metabolic pathways. What we observed was that on the whole, the presence of the drug molecules we chose did not lead to significant changes in the metabolites produced, with the exception of a slight increase in the production of propionate in the presence of 5-fluorouracil, which is a potent chemotherapeutic agent. When we investigated the colonization of the starch hydrogels in the large intestinal phase, we noticed select species, namely Ruminococcus bromii and Bacteroides, both established primary starch degraders, were invading the starch matrix uninhibited, whereas bifidobacteria appear to be clustering in larger colonies along the periphery before invading inwards. The colonization appeared to be time-dependent, where there were fewer bacterial species in the early stages of fermentation compared to the latter ones. These observations were irrespective of the starch type, where the only difference was that the less digestible and less fermentable starch type appeared to be more slowly colonized by bacteria in the gut. We believe this is the result of the differences in the matrix morphology, where the normal maize gels exhibited large cracks and open channels in their surface, unlike Hylon 7, which appeared to have a more uniform morphology, resulting in a decreased accessibility of bacterial species. So in summary, so far in my work, we have shown the INFOGEST protocol's applicability to pharmacological and pharmaceutical contexts. We have demonstrated starch hydrogels' viability as orally administrable targeted colonic drug delivery vehicles. We have shown how starch gel structure and organization governs their pharmaceutical excipient properties. We have shown how we can modulate our choice of starch to fine-tune the pharmacokinetic profile of the drug molecule. We have quantified starch hydrogels' auxiliary gut health-promoting properties, namely the production of short-chain fatty acids, and we have probed the interactions with the gut microbiota. And with this, I'd like to thank you for your attention. I'm more than happy to answer any questions you might have. But first, I'd like to express my gratitude and appreciation for my 2 research groups, both the one at Quadrum and at the School of Pharmacy at UEA, to my supervisors, Dr. Fred Warren and Professor Jaroslav Kimiak, for their support and the degree of freedom I was given during my PhD, and to the postdocs, Dr. Hannah Harris and Dr. Juan Carlos Muñoz-Garcia, for making sure I didn't kill myself with the column models and the NMR spectrometers. Thank you for your attention.
Thank you very much, Trey, for a very interesting overview talk. It's leading, from everywhere. Really interesting. Thanks a lot. First question to you. How about the pore size of the hydrogel study? You've shown some slides, but how was the intention at the beginning of your study on the pore sizes?
So in terms of pore size, the only kind of data that we had was purely based on the microscopy data. So what we saw was that there was an increase in pore size. And for example, specifically in the case of Hylon 7, where we start with this kind of more uniform, cohesive gel morphology without any kind of cracks or crevices or pores. At further fermentation stages in particular, towards the 48 or 72-hour fermentation, we were noticing slight appearance of channels or openings or pores in the morphology. And they were significantly smaller compared to normal maize, which even in the beginning stages of fermentation, it already had these kind of cracks and openings in its structure. So it was far less cohesive, like I mentioned in the microscopy slide section. In terms of diameter, change of diameter, just because it's not a very homogeneous, the gels are not very homogeneous in the sense of pores throughout them. So you have differential sizes of pores throughout their whole gel morphology. It's difficult to kind of say, if there's a particular type of pore size throughout the gels, but we can say firmly that the pore size does actually increase as the gel is being digested or fermented. We were thinking of doing something like gas absorption to measure like the actual surface area of the internal pores, but again, because it's not a homogeneous structure in terms of there is no uniform size of pores inside the actual matrix, it is difficult to actually obtain gas absorption data.
All right. Then I have another question for you. In terms of the mechanical strength, was the fracture stress of the gels assessed?
Yes, so we were looking at, I would bring back that slide, but we were looking at the actual point of loss of structural integrity, which we were kind of quantifying by the crossover point of its G prime and G double prime. And what we were noticing is that, yes, as the gels were being digested and fermented, that was progressively getting weaker and weaker in terms of the G prime value anyway. So in other words, the exact point of break or loss of structural integrity was dropping in terms of G prime value.
Another question from myself is about the drugs that you try to then integrate into the matrix. So that would be potentially affected by the digestion as well. Is there any specific properties of the molecules that you can choose in order to protect them in the starch network?
So when we were first thinking about loading these gels with drug molecules, obviously one of the first things that we wanted to know was whether the presence of the drug was going to in any way change the gel structural integrity, because obviously that was going to, because the release profile is very matrix degradation dominated in terms of kinetics. We wanted to not lose any of the matrix integrity, not change in any way. But in terms of choosing the actual molecules, what our primary reasoning for choosing those three in particular was we wanted to pick out three molecules with different physical chemical properties, namely like their ability to hydrogen bond, how hydrophilic or lipophilic they were, their varying size as well, including more electronegative elements such as fluorine in the 5-fluorouracil as well. But in terms of actual protection from the enzymes, from what we saw, there was very little release in the upper gastrointestinal tract of the small molecules. So from what we can tell, the drug molecules are actually located within the actual inner parts of the gel matrix. So they are in a way protected by the gel itself. So because the gel is resistant to upper gastrointestinal tract digestion, these small molecules are also remaining within the integrity of the gel, only to be released in the large intestine where the gel is fermented by the gut microbiota. Sorry, does that answer your question?
Yes, thank you.
Okay, cool.
Very, very nicely done. And one last question, maybe before we move on. Why does the bifidobacteria colonize gels differently to the other bacteria types?
Yeah. See, that is something that has been on our mind for the past maybe 3 or 4 months. And one of the things that we have as potential explanations, and by no means is this like a firm reasoning behind it, but from the data that we have seen or from previous publications, we know that the bifidobacteria tend to be largely cooperative. So they may rely on different strains of bifidobacteria to form in larger colonies, form these kind of, I guess, biofilms towards the periphery of the gel, and only then start invading inwards, relying on more of a cooperative aspect. But again, that is by no means evaluated or troubleshot, I suppose. Yeah. So just a hypothesis in working, I suppose.
All right. One more question, maybe shortly. Were you surprised that the drugs did not influence the fermentation so much?
Honestly, yes. One of the things that I was kind of expecting to see is a significant loss or significant drop in the amount of short-chain fatty acids and some other metabolites, because we did screen for other metabolites as well, but I only included the short-chain fatty acids as gut health promoters. But one of the things that I was expecting to see was primarily a drop in the production of short-chain fatty acids in the presence of 5-fluorouracil and doxorubicin, just because they're such potent chemotherapeutics. And by means of their action, they're largely topoisomerase 2 inhibitors. So I would have expected to see, just because by means of their action, they do inhibit DNA transcription and translation. So what I wanted what I was expecting to see is a drop in the production of metabolites, just because I would have expected them to nuke bacteria as well, you know. But yeah, I was surprised that there wasn't a significant drop in the production of metabolites. Even more so, the slight increase in propionate in the presence of pyrethroiosol. That was something I definitely did not expect. But yeah, I was surprised.
Okay. Thanks again very much, Trey, for this great talk. And we are moving on to our next presentation that is given by Raffaele Colosimo on the impact of mycoprotein matrix on in vitro carbohydrate digestion. Then the screen is yours.
Hi everyone, my name is Raffaele Colosimo and I'm a PhD student at the Quadram Institute Bioscience in Norwich. My PhD project aims to understand how mycoprotein consumption can influence and promote human health. In this presentation, I will focus specifically on the impact of mycoprotein matrix on in vitro carbohydrate digestion. But first, what is mycoprotein? Mycoprotein is the main ingredient of all meat replacement products branded as Quorn. These products are obtained from the filamentous fungus Fusarium venenatum, which is a member of the Ascomycota division. I understand that the composition of mycoprotein can cause confusion, as its name suggests to be a protein, a single macronutrient. However, mycoprotein is far more complex than that, as it is a biological structure which comprises all the macronutrients that are retained within a fibrous cell wall. On a dry weight basis, mycoprotein is high in protein and fiber, which are 44 and 25% respectively. Furthermore, 12% is carbohydrates that are present as glycogen and in limited account as sugars, while 10% is lipids. Mycoprotein is produced by a continuous fermentation process in 40-meter high vessels. This process requires glucose as a source of carbon that is introduced together with biotin and mineral salts. The ammonia as a source of nitrogen is pumped into the vessel with air, which facilitate the movement of the broth to move to the riser. At the top, CO2 is released and oxygen is introduced to keep the flow of fermentation into the downcomer. At the moment of harvest, the fungus moves to the RNA reduction vessel, where the temperature is increased up to 80 degrees Celsius to reduce the RNA content from 10% to 2%. After that, centrifugation takes place to remove excess water. Then, the product is chilled to allow the formation of ice crystals that are fundamental to push the filamentous cells together and help in the formation of the typical meat texture of the final product. As you can see in this image, the mycoprotein microfibrils resemble indeed the chicken breast fibril bundles. At this point, the ingredient is called mycoprotein, which is then mixed with other ingredients to form a wide range of corn products. A crucial component of mycoprotein is the cell wall. The fungal cell wall is mainly composed by fiber, which account to 25% of the total dry weight. 2/3 of the cell wall are represented by beta-glucans and 1/3 from chitin. Other components are glycated proteins. We know from the literature that dietary fiber, which is often enclosed in the cell wall of plants, may have positive effects on human health. For instance, reducing blood cholesterol and increasing insulin sensitivity. We are now discovering that the fungal cell wall can also have similar effects. However, the mechanisms by which fungi promote these effects may differ from plants due to structural differences. For example, chitin is only present in fungi, whereas cellulose and pectin only in plants. The beta-glucans are shared between the two kingdoms of life, but differ in the beta links, which see the 1,3,1,6 beta links in fungi and 1,4,1,6 in plants. Focusing on the mycoprotein literature, research over many years have found that mycoprotein can have several positive effects on human health. For instance, mycoprotein has shown to have high protein bioavailability, to reduce insulin and glucose responses, as well as blood lipids. These studies observed the physiological effects in vivo, but the biochemical mechanisms which lead to these health effects aren't clear. That's where my PhD project takes place and aims to understand these processes with an in vitro approach. Today, we will focus on the study that I carried out to understand the biochemical processes that underlie the reduced insulin and glucose responses. In the carbohydrates metabolism, we know that the absorbed sugar from the small intestine can reach the blood. The pancreas is crucial for maintaining glucose homeostasis, as it releases insulin into the blood to promote cellular take-up of glucose. Glucose can be then stored as glycogen in the liver and skeletal muscle. Overall, these physiological processes lead to blood glucose level declines. Foods rich in dietary fiber have shown to reduce insulin and glucose responses on different fronts. For instance, by slowing down digestion, triggering hormonal responses, or increasing viscosity in the gut. This work focuses on the intestinal digestion of carbohydrates, and the hypothesis is that mycoprotein can reduce the starch digestion in the small intestine by reducing the amylase activity. This, in turn, will lead to a lower stimulus due to the low level of glucose in the blood. To test this hypothesis, first, the digestion of the glycogen retained within mycoprotein was compared to extracted glycogen digestion following the INFOGEST protocol. This experiment was done to see if the cell wall can influence digestion. Then, a kinetic in vitro digestion with low amylase activity was carried out to observe the kinetic of starch hydrolysis in the presence of mycoprotein. This experiment was planned to test the ability of mycoprotein to reduce starch hydrolysis. The reducing sugar released from the carbohydrate source were measured with PAB assay, which is a colorimetric method. The ENS-check assay is based on fluorescence spectroscopy, and it was used to estimate the residual amylase activity. Confocal microscopy was used for imaging the mycoprotein cells and the alpha amylase diffusion through mycoprotein cell walls. In this graph, mycoprotein and extracted glycogen were digested in the small intestinal step of the INFOGEST protocol. The reducing sugars measured with PAB assay were expressed as glycogen hydrolysis. The mycoprotein glycogen that is retained within cell walls has a slower digestion compared to extracted glycogen that has no cell walls and it is already available. Besides this information, the INFOGEST digestion was also carried out in order to remove the intracellular glycogen from the mycoprotein matrix. This was done to remove the source of carbohydrates from mycoprotein that could have interfered with the next experiments in the presence of a starch solution. However, the digestion with 200 units milliliter of amylase was not enough to remove completely the glycogen, but doubling the activity, the glycogen appeared completely digested after 2 hours. A solution of 5 mg/milliliters of starch was digested in the presence of increasing mycoprotein concentrations for 12 minutes. The starch hydrolysis decreased significantly with the addition of increasing mycoprotein concentrations, and 2.5 mg/milliliters of mycoprotein were already enough to have a significant effect. The same starch solution was digested with mycoprotein protein isolated. This time, only a modest hydrolysis reduction was observed and was lower compared to effect promoted by the whole mycoprotein matrix. The residual alpha amylase activity was then measured and expressed as bound alpha amylase. This experiment was carried out by adding the enzyme in solution with increasing mycoprotein concentrations. What we observed was that the more mycoprotein you add, and the more alpha amylase is bound to mycoprotein, and hence removed from the solution. By removing the enzyme from the solution, the activity is consequently decreased. Confocal microscopy was used to further investigate the binding of alpha amylase to the mycoprotein matrix. Fluorescent dye stains in green the internal content of mycoprotein cells, whereas calcolor white stains in blue the cell walls. When mycoprotein is incubated with the fluorescent label amylase, you can see that the label enzyme is present as green spots in some location of the mycoprotein cells. We can also see the thickness of the filamentous cells by Z-stacking. Z-stacking is a digital image processing method that, by combining multiple images at different focal distances, it provides a composite image with a greater depth of field. This confirms that the location of the enzyme is inside the cells and suggests its diffusion through the mycoprotein cell walls that results in a sequestration from the solution. This confirms that the enzyme was bound to mycoprotein, and by being removed from the solution, the starch hydrolysis was then decreased. The interaction between mycoprotein and alpha amylase was investigated with kinetic analysis to understand the type of inhibition. Kinetic analysis showed that the inhibition of amylase is of a mixed type, as suggested by the alteration of both Vmax and Km in the Michaelis-Menten plot. Indeed, Vmax decreased, while the Km increased at the increase of mycoprotein concentrations. Similarly, the Dixon and Cornish-Bowden plots confirm this observation by showing the typical behavior of a mixed type inhibition, with the intercepts that are in the fourth and third quadrant respectively. The mixed type inhibition suggests that there is not a specific binding of mycoprotein to the enzyme, but more likely supports the sequestration of the enzyme within mycoprotein cells observed with confocal microscopy. To summarize, this study identifies potential mechanisms underlying the reduced glycemia and insulinemia reported after mycoprotein consumption. It was found that pancreatic alpha amylase can diffuse through mycoprotein cell walls thanks to its porosity permeability. The presence of mycoprotein cell walls may slow down the kinetic of carbohydrate digestion. Starch hydrolysis was reduced due to the sequestering of the enzyme within mycoprotein cell walls. Mycoprotein proteins may also play a minor role in the inhibition of alpha amylase, and these results can be adapted by the food industry in processes with the aim to reduce starch hydrolysis. And with this I conclude, and I would like to thank my academic supervisor Pete Wild, Fred Warren and Kat Edwards, and my industrial supervisor Tim Finnegan. I would also like to thank people in the lab that helped me through this journey, and thanks all of you for listening.
Thank you very much, Raffaele, for this very interesting presentation. We have a number of questions. So one question from Patricia Rasmadiero is, are the fungi still alive in the food product? And in which case, have you checked for its survival after digestion and its interaction with the colonic microbiota?
Hi. Well, no, the final food products, there are no fungi alive, so the cells are, after all the process, so there is no, in the final product, in the corn that you eat, there is no cells alive. But we are interested in checking the interaction with the colonic microbiota of the products of the mycoprotein per se, the pure ingredients, even though it's not alive, but we are interested in that step.
Thank you, Raffaele. And is the inhibition of amylase or the binding to the mycoprotein specific to, specific as it were, to specific components? And do you think a second part of this question is, do you think that these inhibitory components increase during processing?
Yeah, that's one of the reasons why the kinetic analysis were done to understand the nature of this inhibition. So because what we observed, there was this reducing of starch hydrolysis, and also with the microscopy, we also saw that mycoprotein bind to mycoprotein, but it was actually inside the cell. So we wanted to see if this interaction was just on the cell wall or it was entrapped within the mycoprotein matrix. And also by the binding of the enzyme that we observed that the amylase activity was reduced. It seems that the enzyme is sequestered by the enzyme. We don't know if there is a specific interaction with components, but also there was this interaction with the protein isolated. So with the protein isolated, we also see this effect. So it suggests that can be some specific interaction. However, also the inhibition was of a mixed type. So this suggests that it can be, it's not a competitive inhibition which binds specifically to the active site. So this suggests that it's more like sequestering of the enzyme.
Okay, very, very good answer. And I guess about the mixed type inhibition, did you check for the presence of other amylase inhibitors?
No, it was done only on with the amylase, the intestinal amylase.
Okay, I have a question from the audience from Molly Muleya. She says, you mentioned that mycoprotein has high protein digestibility. Is there an explanation for this, considering the high fiber content, which normally decreases protein digestibility of these kind of ingredients?
Yeah, well, the in vivo studies been carried out several clinical trials, and they show that it's high protein bioavailability. And we did some similar studies in vitro to understand the mechanisms, how the protein are released, and actually we couldn't reproduce the same effect in vivo with the in vitro model. We actually saw a limited protein release, but we were more focused on the mechanisms. So yes, because I understand that the fiber, actually the cell wall can limit the release.
Thank you. We will have another question from Andrea Gianotti about the specific fungi species. So you have used a specific fungal species. Do you think that the same behavior might be observed for other fungi? Have you tested other fungi species and seen the same effect?
So the core products are all obtained from the same strain of this Fusarium venenatum. So it's they cannot change with other strains. But there are other products that can be developed with other types of fungi or also with different strains. But I haven't tested because I'm always use the same strain that you use for mycoprotein in the final product for all the core. But yes, it's definitely an interesting point that maybe different fungi with different features, with differences in the cell wall as well, can have different digestibility.
Thank you. And you might have said this already, or in your presentation, but did you measure the porosity of the fungal cell wall using, for example, FITC markers and so forth?
It wasn't tested the porosity. It was with the microscopy, the confocal well, it was to see if there was this permeability, porosity, but it wasn't specifically measured.
Okay, thank you. And then just a final technical question about why did you choose 0.2 units per mil in your inhibition assays?
That it was done to reduce from the 200 units milliliter of the protocol that was quite high. So if I had a high amylase activity, I would not have had a linear response for my kinetic analysis. So it was decreased, and it was 0.2. It's not just because I diluted to have this linear response in 12 minutes. It could have been even more, but the important it was to be linear. So it's not the important. It was that it was a low activity.
So do you think that the inhibition will still be biologically significant in a kind of human system?
Yeah. Yes. It can be.
Excellent. Thank you. I don't see any other questions. So I think we're going to thank you again, Raffaele, for your talk and your excellent answering. And we're going to move on to our next speaker, who is Jennifer McClure. And she's going to talk to us about the use of chickpea red lentil formulations and how they affect and mediate starch digestibility in third-generation extruded snacks. Let's listen to her presentation. Thank you.
Hi, I'm Jen, an IK student in the Warren Lab at QIB working with PepsiCo. I'm going to talk about the use of chickpea and red lentil incorporation and formulation water and how they affect starch gelatinization and mediate starch digestibility in third-generation extruded snacks. So as we all know, pulses are high in a number of nutritional properties and are an excellent source of protein, vitamins, dietary fiber, and complex carbohydrates in the human diet. Pulse starches are also more slowly digesting in comparison to potato starch, so incorporating pulse ingredients into a snack could make them more slowly digesting and healthier. However, they also behave very differently to potato starch during processing. The structure and the way that they bind water is different, which can lead to differences in gelatinization. So these are some of the challenges involved in processing a pulse-based snack. The process that I used to incorporate pulse ingredients into my snacks was extrusion. So here I took the raw mixes and put it into this heated screw, and as it passes through the screw it undergoes cooking and mechanical shear, which breaks down the structure and causes structural changes, so we get a plasticized material at the other end, looking somewhat like this, and that can be expanded in a second step to become more the final product that we all know. I'm interested in looking at how formulation moisture and incorporation of ingredients such as chickpea and lentil flour affect starch digestibility in snacks. So to look into that, I produced a series of samples containing different pulse incorporation levels and different moisture contents. I then measured the gelatinization and starch digestibility of the raw materials and the extrudates and the final products, so that I could hopefully understand how the degree of starch gelatinization influences starch digestibility. Before producing extruded samples, I carried out preliminary work to determine the optimum formulation for water content. I analysed a series of samples containing the dry mix at different levels of hydration on the DSC. I was interested in samples that were partially gelatinized, as the open structure would allow for expansion later on, but not fully gelatinized, as starch granules are needed for expansion. From the results, I decided that these samples at 25 and 35% were of most interest. I also analysed raw ingredients as pure, so not within the mix. Here we can see my potato starch. You can see that gelatinization starts at around 60 degrees for the higher moisture samples, but with the low moisture at 25%, it requires a higher temperature before we start to see any sort of peak. This also helped me to determine the temperature at which I ran the extruder. With the pure red lentil flour samples, we can see that the gelatinization peak here is very small, and the change in moisture at 25, 30, and 35% makes quite a small difference in the gelatinization temperatures. The change in moisture here, 25, 30, and 35%, does make quite a large difference in the dough, however, with the high moisture dough looking more like a batter. When looking at pure chickpea flour, I focused on the extremes of moisture content I was interested in at 25 and 35% moisture. I found that the onset temperature for gelatinization was fairly similar between the low and high moisture. However, the profile was quite different, with a large shoulder observed in the high moisture sample. Again, the moderate increase in water content resulted in quite a change in the look of the dough. These are the series of samples that I produced. I had a negative control containing 0% pulse flour, then either 10, 40, or 80% of either chickpea or red lentil flour. To these mixes, I either added 25% water or 35% water as low and high moisture. And these are what the doughs look like prior to extrusion. So we've got chickpea on the left here and red lentil here. And I'm just showing the extremes of 10% and 80% pulse incorporation. As you can see, 10% difference in moisture might not sound like a lot, but it does make quite a lot of difference in the dough formulation, particularly in the ones that contain higher amounts of pulse flour. This is the extrusion process that I went through while at PepsiCo. I used a single screw extruder, and because I was making third generation snacks, I ran it at a lower temperature of 80 degrees. Also, you can see that with the high moisture and high pulse formulations, it could be sometimes quite difficult to get the mix into the screw in the first place. And here you can see what comes out the other end, the extrudate. This is of a negative control. This is showing before and after extrusion of some red lentil products. This is the series, which you can tell by the lovely gradient. And before and after expansion, notice that the products that had a lower incorporation of red lentil flour tended to expand a bit better than those that had quite a high incorporation. The method I chose to use was air frying because it uses no oil, which is better for a healthy snack. I optimized this for fry temperature and time to try and produce snacks that had a high amount of expansion that was also uniform. So I decided that 210 degrees and 1 minute 30 seconds was the optimum parameters. I looked at gelatinization using DSC in excess moisture. So here on the left you can see the extrudate samples, and on the right the extrudates that had also been expanded. The samples here are 0%, 10% chickpea and red lentil flour incorporation, 40%, and 80%. And you can see that the L and H is for low and high moisture formulations. So with these DSC measurements, you can see the enthalpies on the colored columns, and it's showing the amount of gelatinization that was still to occur post the processing. So the samples that have a higher number, such as here, that means that not a lot of gelatinization actually occurred during the extrusion process. So a lot of gelatinization happened afterwards. And you can see that the samples that are higher in pulse flour, like all of the 80% samples, have quite a high gelatinization enthalpy. So they didn't gelatinize very much during the processing. I also used XRD to look at the percentage of starch crystallinity of my raw materials and extrudate samples. These were equilibrated at 75% humidity prior to scanning. So with the raw materials, we can see that raw potato starch has higher crystallinity than either raw chickpea flour or red lentil flour. The peaks are quite a lot more defined. When looking at extrudates such as potato starch only, I found that higher moisture extrudates had a higher crystallinity compared to low moisture, as you can see here. When we increase the percentage of pulses in the formulation, we found that the higher extrudates had a lower crystallinity, which was expected based on the raw materials. And we also see this extra peak that arises from the pulses. When comparing the starch crystallinity to the total enthalpy of the raw materials and extrudates, I found a positive correlation, which indicates that starch crystallinity is related to gelatinization. With the samples produced, I then wanted to look at the starch digestibility. So I used this digestion method, which is a static digestion, and uses alpha amylase as the sole enzyme. I carried it out using the series of time points, and you can see that they are quite frequent in the beginning and then start to get a bit longer as the digestion progresses. For most of my samples, I stopped the digestion at 150 minutes. However, for the raw materials such as potato starch, chickpea flour, and red lentil flour, I ended at 330 minutes, simply because they digest incredibly slowly, and you can see that even at 330 minutes, there is not a lot of digestion that has occurred. And you can see that potato starch digests much less than either of the pulse flours. When looking at the starch digestibility of the extradates, I found that a 10% pulse incorporation had little effect on the digestibility. You can see that it's slightly less digestible, but not by much. And on the right here, you can see a loss plot, which shows the kinetics, and there is not much difference in the 10% pulse incorporated extradates compared to the potato starch only. When we look at extradates that have a higher incorporation of pulses, however, we can see that the addition of pulse clearly has effect on the starch digestibility. When looking at the expanded snacks, we can see a similar trend. So the C infinity is the calculated starch digestibility endpoint, and we can see that increasing the amount of pulse flour leads to a decrease, and this is seen across all of the samples in chickpea and red lentil flour and in the low and high moisture samples, more so in the chickpea. When comparing between the calculated digestibility endpoint and the gelatinization enthalpies of expanded snacks, there is a strong correlation to be seen, which indicates that gelatinization has an effect on how well the snacks are digesting. This is exciting because if we can control the gelatinization during processing, then we could affect the starch digestion. So to summarize, a higher moisture content during extrusion results in increased gelatinization, whereas more pulse incorporation decreased gelatinization. This is possibly due to the water holding effects of the pulses, meaning that less water is available for gelatinization. With starch crystallinity, we found that both processing through extrusion and the addition of pulses decreased starch digestibility. Addition of pulses was also found to decrease starch digestibility at both low and high moisture. In terms of the impact of starch gelatinization on starch digestibility, a strong negative correlation was observed between the C infinity and the gelatinization enthalpy of expanded snacks. So it's possible that by controlling the gelatinization during snack processing, we can affect how well the snack digests.
Thank you very much, Jennifer, for a very interesting and snacky talk just before lunch break. Great, thanks a lot. I got a couple of questions for you. Let's start with coming back to the gelatinization and the moisture content. So it's true that the starch is not fully gelatinized at the low moisture content, right?
Yes, that is true.
Okay, and then we have a question from Anaïs Lavoisier in the chat function. Hi, Jennifer, how does this reduction in starch gelatinization influence the organoleptic properties of the snacks?
Thank you for your question. I'm not sure about that, but that is something that would be interesting to look into.
So you haven't tried them.
If we're looking at the texture, the reduction in the starch gelatinization causes the higher pulse incorporated snacks to not expand very well.
Okay. Then we have another question from Ruud van der Sman. A strong correlation between digestion and crystallinity is not surprising and independent of ingredients.
Independent of ingredients, I think
my connection is a little bit blurry here. Could you hear me?
Yes, thank you. I think yes, it could be independent of the ingredients, but also the way that because of the ingredients, it changes through the difference in water holding.
Yeah, you have shown this nice correlation with the moisture content. One more question. What components in the pulses retain the moisture?
I think because of the increase in the fiber and the cell walls in the pulses is very different to the starch granules, then it means that they hold the water more. They take in water, and there's less available for the potato starch.
And did you also look into the effect of the lipids and protein from the lentil and the chickpea on the starch gelatinization before and after extrusion?
I haven't yet looked into the protein, but that is something that I'm interested in the future that I'm moving on to.
Okay, and another question on the extrusion process itself. So you used always kind of the same outcome of for the extrusion, or are you also going into looking at different like surface buildups during the extrusion as well?
I used the same process every time.
Yeah. Are you going to look into like different surface structures as well, how that would impact?
That would be interesting, yes.
All right, thank you. Let me see if I'm missing out any questions. I hope not. See in the Q&A session again. Otherwise, you can still answer the questions that come from the audience at any time later on. I hope I had everything. Then Jennifer, thank you very much again for interesting talk, as I said, with the snacks just before lunch break. And I'm closing the session with Caroline.
Thank you very much. And Nadia and I want to thank all the speakers for their excellent talks, and also the audience for engaging and for your attendance and questions. Please remember to keep an eye on the INFOGEST social media for any future starch related events. So thank you very much. And I think I'm handing over back to André.
Yeah, excellent. So thanks again. Thank you, the session chairs and all the speakers. We have a short break now for about 20 minutes. So we start again 12:05 Irish time, which is in about 25 minutes. We're in the home stretch, so bear with us. Okay, it's 14 hours, so we are on the last hour now. So here we go. Thanks a lot. Yeah.
Thank you.
Bye.
Welcome back. We are nearly there. Welcome to our last session. We have a number of session chairs, Stephen Lafontaine, Choi Hong Lai, and Didier Dupont. If you can show yourself, excellent. And without any further delay, I hand this session over to you.
Thank you, André. Good afternoon, everyone. Very pleased to be there for the last session. So I'm Stephen Lafontaine, working at INRAE in France in the team of Didier Dupont. And I'm co-leading the in silico working group with Choi Hong Lai. And so during this last session, we will have two different topics. One about the modeling of in vitro of food digestion, and the second one on gut microbiome. So two talks for each topic. Choi Hong, do you want to introduce yourself? Your microphone is mute.
So my name is Choi Hong Lai, and I am co-chairing this session with Stephen. And I will talk to you from University of Greenwich in London.
Hello, everybody. My name is Didier Dupont. I'm senior scientist working from INRAE in France, and I'm also the chair of INFOGEST.
So we'll move on to the talks now. Maybe just reminding that the gut microbiome topic that we will be about so in half an hour from now will also be a topic of the next conference in Cork next year. So there should be place to have a talk and abstract on that topic. So don't forget, this is a sort of new topic in INFOGEST, but there will be places in the next conference on that topic. So now let's move on the first talk by Sarah Verkamping. So Sarah is in her 2 years of postdoc in the laboratory of food technology at the Catholic University of Leuven. She did her PhD in the same place, during which she focused on lipid digestion of emulsified lipids. And she also started to develop modeling approaches during her PhD. And she's now an active member of our working group on in silico modeling, and was involved in the writing of one of our review papers on the modeling of macronutrient hydrolysis during in vitro digestion. And her talk will be about that paper mostly. She will give a preview of the way the way of thinking that is given in that review paper. So I'll let you now start the video.
Hello, my name is Sarah Verkamping. I'm a postdoctoral researcher at the Lab of Food Technology at KU Leuven. And today I would like to explain you why mathematical modeling could be of interest for you. As all of you know, food provides energy and nutrients to the human body. Today I would like to focus on the three macronutrients, lipids, starch, and proteins. They are hydrolyzed by a range of enzymes in our body into intermediate digestion products and eventually absorbable nutrients such as free fatty acids, maltose, and amino acids, for example. Understanding the fate of these macronutrients in the human body became a very active field. In most cases, static in vitro models are employed to study digestion kinetics and how they are impacted by, for example, food design factors. In these static models, the pH is kept constant, as well as the enzyme concentrations used, and no transit is actually considered between compartments. The advantage of these static models is that they are relatively simple, as they are well controlled. Therefore, they are very interesting to use when studying a large range of food design factors, for example. However, the conditions used are not always considered physiologically relevant or relevant enough to obtain, for example, digestion kinetics, which are also valid for the in vivo case. Therefore, a number of dynamic in vitro models were developed. In these cases, particular factors change as function of digestion time, such as pH and enzyme concentrations. Besides, transit is also often considered in these dynamic models. These models can thus be considered more physiologically relevant and can thus result in kinetic data which are relatively close to in vivo conditions. However, these systems are not easy to interrupt to study, for example, the enzymatic hydrolysis as function of digestion time, and also data interpretation is much more challenging in comparison to static models. More recently, semi-dynamic models have also been developed, which can give a solution to particular issues, such as interrupting the system to sample. But also, it can make the data interpretation a bit more simple. In terms of data interpretation, mathematical modeling could serve as an interesting tool to quantify macronutrient hydrolysis, for example, to interpret data, but also to test particular hypotheses on digestion mechanisms, for example. Unfortunately, mathematical modeling is only scarcely considered in the in vitro world, mostly because of a lack of know-how. Sometimes also there is the misjudgment, for example, that you need a very strong mathematical background, but also, we do not always understand the added value of modeling, for example, the in vitro data. Within the INFOGEST network, and especially Workgroup 6, some initiatives were taken to show what mathematical models could do. The initiative I was involved in was writing this review paper on the mathematical modeling of food hydrolysis, together with some colleagues from different research units over Europe. It was a long journey, but we are happy to announce that we submitted this paper a while ago to the Journal of Trends in Food Science and Technology. And we are now waiting for hopefully good news soon. In this paper, we discussed different concepts, from static over semi-dynamic over full dynamic digestion models, but we also considered food systems in which only single nutrients were present over more complex food systems. This is also what I'd like to show you today in a more illustrative way. So how particular cases mathematically can be modeled and what additional insight this could give. During my PhD, I studied the impact of different emulsion properties on the lipid digestion kinetics. It means I also have a stronger knowledge or background in food technology rather than in mathematical modeling. However, along my PhD journey, we started to model the data I obtained, starting from some basic regression towards, in the end, a more complex multi-response model. This is also the first example I would like to show you. And by sharing my experience, I hope also that I can show you that this was also a learning process for me. But back to science. In this example, you see the data points obtained for 5 emulsions, stabilized by different emulsifiers and studied in a static in vitro gastric phase. Each digestion point corresponds to 1 repetition, as the digestion was performed in independent individual tubes. If we have a look at the overall trend of these data points, we see first an increase in the TAC hydrolysis, followed by a plateau value reached at different time moments in the gastric phase for the different emulsions studied. By making use of model discrimination, which actually means you try several types of models, such as the first or the zero order model, you try to find actually the model that is best describing your data. In this case, it was a fractional conversion model. This model gave us 2 parameter estimates, a rate constant K and a final concentration CF. This type of modeling is also called empirical modeling, as we just selected a model based on our observations rather than a theory. You can do it for each case you study and compare the kinetic parameters obtained in a more quantitative way to evaluate several conditions under investigation. Another approach you could follow for these relatively simple emulsions is to try to find a multi-response model. This type of modeling takes into account multiple digestion species that are quantified. So in this case, not only the triacylglycerols, but also the monoacylglycerols and free fatty acids, for example, which are interlinked by a common reaction network. As we all know, TACs are hydrolyzed to eventually form MACs and free fatty acids, so these nutrients are part of a common chemical reaction network. Briefly, multi-response modeling consists out of 4 important steps. First of all, you have to have a look at your data and try to see trends. But also you can have a look in literature to find some information regarding the reaction mechanism. In a second step, you can propose a reaction network. In this case, we kept it rather simple, And just to note, I switched here from some data from the gastric phase to small intestinal phase actually, and we only considered here tax marks and free fatty acids. Thirdly, we can transform the reaction network into differential equations. And to be honest, there I also had to dig a little bit deeper again into my mathematical knowledge obtained during my educational training. But lastly, and luckily, these differential equations can be solved by statistical software. And from the output of that, you need to evaluate that. For example, you have to check the convergence of the model, the errors on the parameter estimates, and you can, for example, make a parity plot. A very important remark to make is that this process is an iterative process, so trial and error. When you start to do this, you have to try several models to eventually find the one that is best describing your data. In our case, we also had to make some simplifications, but that was also the starting point for actually new research. The outcome of a very first model, or multi-response model, was this reaction network. And yeah, we can actually state that this model is more mechanism-based and much more powerful than the single response modeling as I showed in the first example. We integrated here multiple lipid digestion species, which are interlinked during the hydrolysis process. Another important aspect that you need to consider is that the parameters you obtain like this are much more meaningful and precise. As I said, this model is from a few years ago and was also the starting point for new research, as we extended our model also for gastric lipid digestion, and we now also include deacylglycerols and radioisomers of, for example, the DAX and the MAX, to gain much more insight even in the lipid digestion mechanism. But next to lipids, we also have starch and proteins, and they are often present together in food systems, such as pulses. In these pulses, starch and proteins are bioencapsulated by a cell wall, and in turn, the protein matrix also surrounds again the starch. If we zoom in into the starch digestion of one particular pulse type, the Bambara groundnut, we see that the static in vitro digestion is characterized by first a lag phase, then a steep increase in hydrolysis, and then a plateau value is reached. A slightly more complex model than in the first example has been used. So here we use a logistic model. This model could nicely describe the behavior and gave us 3 parameter estimates, which we could quantitatively compare among the cases studied. Like this, we could state that the Bambara groundnut that was cooked for a longer time, so the blue curve, had a faster amylase, that the amylase diffused faster through the cell wall to hydrolyze the starch. And in the end, this also led to a higher level of starch digestion for this Bambara groundnut than the one that was cooked for a shorter time. There are many indications that the protein matrix, which encapsulates starch and pulses, plays an important role in this digestion behavior. And if we study the protein digestion kinetics, we also see a faster and higher digestion for this case in which the Bambara groundnut was cooked for a longer time. So for pulses, which might seem logic in the first place, we clearly showed that protein and starch digestion go hand in hand, which is also shown in this plot here. These 2 examples were for static in vitro cases. I elaborated a bit more on those cases as I still think that most researchers use these type of digestion models. However, we cannot ignore the recent trends of evolving towards more dynamic conditions. The challenges for such systems are, among others, that they have change in physicochemical conditions, but also the substrate amounts decrease and intermediate and hydrolysis products vary as function of digestion time. Lastly, in some cases, transit also needs to be considered from one compartment to another. If we take a very basic example consisting out of one reactor without transit, we know actually the amount of fluids, in this case gastric fluids, we add. You know the amount of enzymes that are added at each time moment, as you control this by pumping a known concentration of the enzyme with a known rate. We also know the amount of acid being added, as that is monitored, but most of the time also the pH is changing in this case, and we monitor this most of the time by a pH meter. What we don't know is the buffering capacity of our food, but actually that's not really important as you monitor closely the pH. The real thing we don't know, taking into account that the food structure effects in this example are negligible, is the pH dependency of the enzymatic activity. Luckily, many people studied already the enzymatic activity and how it was impacted by a changing pH value. So we can model this into curves like this. In this case, for the gastric phase, we see at a pH of 3, that is currently used in the static INFOGEST model, is that alpha amylase has almost no activity, and pepsin and gastric lipase have an activity around 50%. When we translate this into an example where the pH profile looks like this, we can easily know the enzymatic activity of each enzyme at each time moment during gastric digestion. For mathematical modeling dynamic or semi-dynamic digestion, the main challenges might be particular food properties, such as food structure effects, rather than the changing conditions. With this, I would like to summarize the most important messages of my presentation. One is that in vitro digestion and mathematical modeling are complementary methods. Mathematical modeling is also a very powerful tool to interpret digestion kinetics in a more quantitative way. And they could also allow to gain more mechanistic insight in the enzymatic hydrolysis occurring. But since this field of mathematical modeling is rather young, much more can still be explored. And both in vitro and in vivo raw data is of interest to build mathematical models to better understand particular effects or interactions that occur during digestion. By further exploring this field, we could step by step advance towards a more complete in silico model that could offer an alternative to experimental studies. And last, but for sure not least, we hope by giving you more practical examples in presentations like this or in the webinars, and by writing reviews as we did within this working group, we could make food scientists more enthusiastic to use mathematical modeling approaches or to search, for example, for collaboration with more experienced researchers in this field. And as a very last thing, I would like to thank the organizers for this nice initiative and for the opportunity to have a talk here. I also would like to thank my lab and especially the digestion team of LFT for the nice collaborations in the past years. I would also like to thank the INFOGEST network, which allows to meet people with this common interest, and this eventually led actually to interesting collaborations already for me. And lastly, I would also like to thank the co-authors of this review paper, and from which I used some interesting graphics. Thank you very much.
Thank you very much, Sarah, for this very nice talk. Before jumping into question, it's not really a technical question, but because you talk about this during your presentation, can you just give us a feeling, a feedback on how difficult it is to jump into modeling when you are not from that background?
It's a while ago, but yeah, in the beginning it was not that easy because you need to take into account some boundary conditions, for example, which I was not familiar with yet. But yeah, it's a learning process. So if you have some good people who guide you through it, it can really be of great help. And I was lucky to be in a lab that had some experience. So it went quite smoothly. But I think for people who would like to go into modeling and they don't have really expertise, maybe look for some collaboration, because it can be, it can help you through it.
Okay, thank you. And maybe a small comment is just to say that the review paper we have been writing with many people is really designed for food scientists, not people experts in modeling. So more a call, an invitation to jump into.
Yeah, indeed, that's true.
There is a question from Ruud van der Sman. He's saying the pH inside food can be different from the gastric juice. and there's enzyme activity inside gel. The charge of protein determines the difference of pH. So how to model all of these?
Yeah, that's the example I did not describe because it's a bit more complex, of course. I know that we explain an example in our review paper. I don't know, I can't remember exactly how it went, but I think you need to have a little bit an idea of how the pH is changing from the environmental fluids inside your particle, for example. And if you have a little bit an idea on that, I think it can go more smoothly to also model that. But how exactly, I think maybe wait for the paper and read it.
Yeah, there is a new question from Pete Wild, quite similar, saying that the idea around semi-dynamic model, so could the change in pH be extended to heterogeneous systems where there is a spatial distribution of pH within the food bolus, so pH gradients?
Yeah, I think it should be possible. But for example, the changing pH is something that is recently used in terms of in vitro digestion. So I think we need some rather basic data first to have a little bit more insight in how kinetics are changing and how is digestion affected by this changing pH. And if we know that, we can go a step further and try to model that. But I think that's the first thing, that we need some basic data on digestibility, on pH changes, and so on. That's really important to have these data.
Yeah, thank you very much, Sarah. And just to complete, I can say that there are some mechanisms that are extremely difficult to model, but our point is more to say that simple things can be done also, and we should try to start with that for advancing towards more complex mechanisms. So thank you, Sarah. It's time to move to the next speaker. Thank you very much, and thank you for the question. So now I will leave the screen to Choi Hong.
Good afternoon, everybody. So this is the second talk of the section 7 in silico food digestion models and the gut microbiome. The title of the next talk is Statistical Modeling of in vitro pepsin specificity. And the speaker is Ousmane Souareg from INRIA Agro Campus West in France. Ousmane, if you are ready.
Good afternoon to everyone. Today I'm pleased to present you a study conducted as part of my PhD, a PhD between food science and statistics directed by Françoise No and David Kozer. My work consists in bringing statistical tools to efficiently answer to food science issues. In this study, we try to identify and order the key factors that influence the working mode of pepsin during digestion. This study is part of the aim of understanding digestion, which consists of multiple steps, in general terms, the oral phase, the gastric phase, and the intestinal phase. A better understanding of these steps will make it possible to design foods according to a nutritional objective, for example, to promote the release of cytogenic elements. Enzymes are the actors of digestion that will reduce the food by successive cleavages. So in the aim of understanding digestion, it is essential to determine in each stage how the several enzymes work. And these enzymes particularly differ in their specificity, that is to say, in what they cleave. I will illustrate this point later in the presentation. In my PhD, we were interested in the gastric phase, and particularly in pepsin, which is the first enzyme that acts on proteins. Unlike other enzymes, the cleavage activity of pepsin is not very specific. Pepsinolysis is even considered in a study conducted by Anne et al. As poorly reproducible. In this study, they found that reproducing many times exactly the same experiment with pepsin could give very different results. Here, you can see the primary sequence of protein and ordered sequence of amino acid residues from the N-terminal side to the C-terminal side, on where peptide bond and amino acid residues are linked to each other by peptide bonds. To define the specificity of pepsin, we'll try to determine why pepsin will cleave an amino acid sequence at a certain peptide bond rather than another one. Now, I'm zooming in on one peptide bond that will be cleaved by pepsin. Each peptide bond is possibly a cleavage site. A peptide bond is defined by the residues flanking it. Conventionally, the residues on the N-terminal side along the primary sequence are at the position called P1, P2, and so on, with the closest residue to the peptide bond being at P1. Respectively, the residue on the C-terminal side are at the position called P1', P2', and so on. Certain enzymes will cleave peptide bond very specifically, that is to say, according to the residue at P1 or P1'. But it's more complicated for pepsin, and until now, pepsin specificity is defined by considering all the residues from the P4 to the P4' position. This table is taken from a large study that was done to define the specificity of pepsin in an exploratory way. For each residue in rows, we have the percentage of cleavage observed when each residue occupies each position from P4 to P4'. For example, 45.8%, nearly 50% of the peptide bonds having phenylalanine at the P1 position were cleaved. Therefore, pepsin will preferentially cleave, for example, just after phenylalanine, whereas the presence of proline seems to disfavor pepsin action. Overall, it seems that the closest residues to the peptide bond have the greatest influence, but also that the residue at P1 has a greater influence than the one at P1'. In the present study, we first provided a statistical setup to assess the specificity of pepsin action. Then we added on evaluated certain notions we consider important. First, we aim to demonstrate that some positions have a greater influence than others on pepsinolysis. Secondly, until now, pepsin specificity has been defined by considering proteins as linear elements, but proteins differ from each other by the structures that this primary sequence will have in 3 dimensions. And in this study, we propose to consider the local 3D environment of peptide bonds by generating variables that will influence the action of pepsin. So for the present study, 6 proteins were individually submitted to digestion in gastric conditions. At T0, the gastric fluid contains whole protein sequences. And after 30 seconds of digestion, samples were taken from each protein solution and analyzed by mass spectrometry. We are therefore able to identify the peptides generated by the action of pepsin. You have here the whole sequence of one of the 6 proteins digested. On the other side, the sequence of 4 identified peptide out of the 78. The sequence of each peptide is matched to the whole protein sequence. We can therefore identify the peptide bonds that have been cleaved by pepsin. And in total, we have approximately 2,000 peptide bonds, including 600 cleavage sites. Here is the simplest model of pepsinolysis we built. by modeling pepsinolysis, we evaluate the probability of a peptide bond to be cleaved by pepsins, that is to say, the probability that Y is equal to 1, sorry. In this first model, we assume that the probability to observe a cleavage only depends on alpha I for the nature of the amino acid residue at P1, and respectively beta J for the nature of the amino acid residue at P1 prime. In fact, in this logistic regression framework, with two classes, one for cleavage, 0 otherwise, we calculate a propensity score for each amino acid residue at P1 and at P1 prime, giving an idea of the propensity of the residue to favor or disfavor pepsin action. We call them propensity scores because when a score associated to a residue is close to 0 for a given position, it means that it doesn't influence pepsinolysis. When this score is highly positive, it means that it favors pepsin action and disfavors pepsin action if it is highly negative. In this study, we adjusted all the models by adding propensity scores for the protein effect with gamma K, knowing that two proteins can be very different in terms of resistance to pepsin. We also imposed some to 0 restrictions on propensity scores so that a residue having no effect on pepsinolysis will have a 0 as propensity score. We propose this kind of graph in which you can see studentized propensity scores associated with each residue when it is at P1 on abscisse, on at P1 prime on ordinates. The novelty compared to the results of AMRO is that we can easily identify the residue having a significant influence on pepsin action without having to look at the p-values. For example, phenylalanine and leucine residue seems to promote pepsin action both at P1 and P1 prime, and that is the opposite for the glycine residue. The other novelty compared to AMRO's exploratory approach is that we can say that 8 out of the 20 residues do not seem to influence pepsin action at both P1 and P1 prime. We have here a graph confronting the observed and fitted probabilities. There is an overall agreement, but also strong disagreement, especially for low values and high values. They show that the model is not absurd, but needs to be improved. To improve the probabilities, we now consider the residue from P10 to P10 prime. We also considered 14 other variables giving information on the environment of the peptide bond. If this red point is represents a peptide bond concerning the peptide bond location and its accessibility, we first considered the secondary structure in which the peptide bond is included. The nomenclature adopted by the PDB was simplified to minimize the number of modalities. As a result, we have only 3 modalities: the helices, the sheets, and the coils. We also calculated the distance between each peptide bond on the nearest coil, and we illustrate the accessibility of pepsin to the peptide bond by the solvent accessible surface area. We also have variables on the local charge on its hydrophobicity around the peptide bond caused by the spatial proximity of certain residues. We consider different radius for the local environment. Finally, we consider the number of post-translational modifications around the peptide bond. We represented here two peptide bonds in red and the two post-translational modification in green and in yellow. For each peptide bond of the protein, we count the number of post-translational modification in the local environment of the peptide bond, and always according to different radius. Here you can see the variables finally kept in the model, the final model. First of all, we confirm previous findings reporting an effect of the residue up to P4 prime positions. The novelty here is that we show residues up to P10 also having a significant effects, but the influence of P10 here is more likely due to its 3D proximity to the peptide bond. Moreover, it is very interesting to observe that except for P2 prime, the N-terminal side has a greater influence than the C-terminal side, up to P7 prime. There is also an effect of the charge on the hydrophobicity around the peptide bond. The secondary structure on the distance of the peptide bond from coil also have a significant effect. As a result, in the present study, we prove the necessity to consider physicochemical and structural variables to model pepsinolysis. We can see here that the fitted probabilities are much closer to the observed one, with a correlation of 0.8. To conclude, with the approach we proposed, it is possible to quickly identify the amino acid residue having a significant effect on pepsinolysis. We demonstrate that other amino acid residue up to P10 also influence pepsinolysis. The importance of physical, chemical, and structural parameters such as local charge and hydrophobicity was highlighted. But however, we have no certainty that the crystallographic structure used for this study are the same as those under digestion conditions, that is to say at pH 3. Finally, this work defined a statistical setup to answer questions about enzyme specificity. On first publication about statistical modeling of in vitro pepsin specificity is under revision in food chemistry. Thank you for your attention.
Thank you for the interesting talk. And I think there are a couple of questions here. So the first question is from Guy Vrait. Why do you take your samples after already 30 seconds and not after 2 hours? So, and do you correct your cleavage site chances for the frequency of occurrence of the amino acid in the proteins and the stochastic chance based on the position of the residues in the sequence?
Hi, it's a good question. First of all, we took the samples after 30 seconds because we wanted to compare the analysis on the results with the study of Hamero, and he took the samples just after 30 seconds. And the second thing is that we use for the 3D environment crystallographic structure on after during the digestion, after 2 minutes, 30 minutes or 60 minutes, we will not be able to compare what we the observation on why we can observe a certain cleavage of a peptide bond because of the structure, the 3D structure. And the second part of the question, do you correct your sites for the frequency? there is a sort of correction with the nature of the protein, because we don't know exactly what is behind this nature of protein. But it is an interesting thing we can take into account. But first, the objective was to know if effectively we can use this kind of approach to define pepsin specificity.
I think, okay, so we can move on to the second question by Roshan Tan. And I think this question is very similar to the first one. So if I can leave you to answer it by email or other means, then I'll move on to one more question. So how can you tackle the pepsinolysis of millet reaction products?
I don't know what is a mineral reaction product, sorry.
Or maybe you can communicate with the person there. I think it's almost time to switch to another presentation now. So I'm going to hide myself and then pass on the camera to
Yes, so we'll go on, and we will change the topic now, since we will start the gut microbiome session. So there will be two talks. So the first talk is done by Elisa Dufault. She's in third year of PhD, and she recently obtained her doctoral candidacy, so she's close to the end. And she's doing her research in the School of Chemistry at the Autonomous University of Querétaro in Mexico. And her talk will focus on metagenomic analysis of microbiota after in vitro pistachio digestion and colonic fermentation.
I'm going to introduce my project, which is called Metagenomic Analysis Reveals Changes in Microbiota Profile of an Obese even ignis chronotype person after in vitro pistachio digestion and colonic fermentation. Overweight and obesity are defined as abnormal or excessive accumulation of fat that presents a health risk. Worldwide, these diseases have significant exponential growth, and in Mexico, 7 of 10 adults present overweight or obesity. This generates high economic costs, and to reduce the effect of these diseases, various strategies have been implemented. However, these have not been sufficient, becoming essential to developing new strategies considering factors such as colonic dysbiosis and circadian alterations. First, it is necessary to know that the circadian clock is an internal timing system that all living organisms develop to adjust our physiological and behavioral response to the cyclical rotation of the Earth. The circadian clock is found in the hypothalamus. However, it is also present in all peripheral tissues. These clocks are synchronized for various stimuli, being the main one, the light. However, it has been reported that food can help to synchronize the peripheral tissues. Hence, an alteration in these stimuli by external factors, such as those to which today's society is exposed, cause a desynchronization of the circadian clocks, known as chronodisruption, bringing negative consequences to health such as sleep disturbances, psychiatric and metabolic disorders. According to the dynamics of the circadian rhythm, 3 main chronotypes are recognized. It is important to highlight the evening type, which has been associated with fewer hours of sleep, unhealthy dietary habits, and a greater risk of developing weight alterations. Also, it has been reported that overweight people present an imbalance in the microbial population of the colon, better known as dysbiosis, which is characterized by many bacteria of the phylum Firmicutes and a smaller number of bacteroidetes. Moreover, circadian alterations modify diurnal oscillation of the microorganisms in the colon, and the associations with the chronotype with the microbiome have been little explored. There is only one report about population of characteristic microorganisms in extreme chronotypes such as morning and evening. A recent tool to counteract the effects of chronodisruption is chrononutrition, which through bioactive compounds present in food, known as chronobiotics, seeks to synchronize peripheral clocks. It has been reported that short-chain fatty acids produced in the colon as a result of the fermentation of dietary fiber, as well as some phenolic compounds and melatonin, can act as chronobiotics, helping to synchronize peripheral clocks and therefore an improvement in chronotype through various mechanisms, including the reestablishment of the balance of microbial populations in the colon. Pistachios are high in fiber and the highest phytomelatonin content reported so far. However, bioaccessibility and permeability of phytomelatonin and the effect of colonic fermentation on the gut microbiome have not been evaluated. Thus, this project aims to evaluate pistachios in vitro, chronobiotic potential, and microbiota profile after in vitro fermentation. We evaluated commercially roasted pistachios with and without skin. Both samples were subjected to an in vitro gastro-intestinal digestion process, comprising the stage of mouth, stomach, and small intestine. The intestinal stage was carried out ex vivo using the rat-Evert intestinal sac technique, considering 3 incubation times. The permeable fraction was obtained within the sac, and the non-digestible fraction was obtained outside the sac. At each stage of the digestion, a sample was taken to quantify phytomelatonin, and the apparent permeability coefficient was determined in the small intestine. The non-digestible fraction obtained from the intestinal digestion of both pistachio samples were subjected to an in vitro colonic fermentation using a human fecal inoculum as a representative microbiota source. Inulin was used as a positive control, and samples were taken at different times of fermentation. The pH of each sample was measured, and the 3 main fatty acids produced in the colon were quantified, and a metabolomic analysis using gas chromatography mass spectrometer was carried out. For the microbiome analysis, DNA was extracted from the initial time and at the 6 hours of fermentation for both pistachio samples using a commercial kit, and a massive sequencing of the hypervariant region 3 of the 16S ribosomal was performed using Illumina technology. It is important to highlight that this is the first report of phytomelatonin bioaccessibility. The results show low bioaccessibility of phytomelatonin on the y-axis in all stages concerning the initial content of these samples. This may be due to the physicochemical characteristics of the molecule at the oral stage, which allows its absorption from this stage. Also, it was possible to observe insufficient chewing, so the compound would not be efficiently released from the food matrix, and interactions are likely to exist of phytomelatonin with components of the food matrix, such as lipids. The lower bioaccessibility was observed in the gastric stage. This may be because indolamines, such as phytomelatonin, polymerized to acidic pH induced by hydrochloric acid. Also, phytomelatonin can interact with components of the food matrix, such as cellulose, and components of the gastric medium, such as pepsin, avoiding its quantification during this stage. The greatest bioaccessibility for both pistachio samples occur in the intestinal stage and increase within the incubation time. In contrast, there is a decrease in bioaccessibility at the colonic stage, suggesting that phytomelatonin is used and metabolized by the colonic microbiota as previously reported for melatonin. The following table shows the changes in the time trend, 15 to 60 minutes, of the apparent permeability coefficients for phytomelatonin. These values are closely simulating the absorption process in vivo in the small intestine stage and are an approach to the bioavailability of these compounds. For both pistachio samples, it is possible to observe that the dynamic behavior of the apparent permeability coefficients is more significant as the incubation time advances. This coincides with the bioaccessibility data obtained, where a greater release of the phytomelatonin is observed with the passage of the incubation time, as we can see in the previous graph. It is important to note that the basolateral to apical flow is greater than its inverse at 60 minutes. So it is expected that this compound will concentrate in greater quantity on the apical side. However, it is possible to observe that the efflux ratio values are between 1 to 2, which suggests an extracellular balance. Both the kinetic data reported in the table above, as well as the chemoinformatics information and an in silico analysis of the phytomelatonin, support the idea that this compound is efficiently absorbed in the small intestine, with a greater possibility that this step occurs through a passive diffusion process, reaching the systemic circulation. The quantification of three main fatty acids produced in the during colonic fermentation is present in this graph. The highest production of these molecules occurred at 12 hours for both pistachio samples. However, the pistachio with skin had a higher production of total short chain fatty acid related to its dietary fiber content, which was higher for this sample. These results are similar to those previously reported for pistachio, and the fatty acid proportional ratio was kept constant, having a higher production of butyric acid followed by propionic and acetic acid, and this in the first hour display a pattern characteristic of the overweight and obese microbiota and is associated with dysbiosis. It is of particular interest to mention that it has been reported that short-chain fatty acid, particularly butyric, can synchronize peripheral clocks, particularly the ones present in the liver, resulting in an improvement of metabolic process in this peripheral tissue. BIP scores have been obtained that estimate the importance of a variable in the projection of a partial least squares regression model. With this data, we obtained the following figure where the metabolites with greater importance are shown, highlighting colonic metabolites of flavonoids, anthocyanins, and phenols, which improve circadian rhythms. It is important to highlight also the presence of indole, the principal colonic metabolite of tryptophan. This is important since walnuts are a good source of tryptophan, and It is a precursor of indolamines such as melatonin and serotonin, which are key molecules in the improvement of the circadian rhythm. 1-butanol is a dysbiotic compound whose concentration decreases with the passage of fermentation time, suggesting positive changes on the activity of the microbiota and its composition, as we can see in the following results. The microbiome analysis revealed that the abundance of Bifidobacteriaceae and Alkaliniaceae increased after the pistachio fermentation at the family level. Moreover, the abundance of Lactospiraceae and Prebotylaceae decreased after the fermentation. The increase of bifidobacteria has been associated with monounsaturated fatty acids such as oleic present in pistachios. At the genus level, pistachio fermentation increased by Bifidobacterium, Doria, Bacteroides, and Parabacteroides. Fermentation of phenolic compounds has been associated with an increase of Bifidobacterium, while Bacteroides and Doria are closely associated with the production of short-chain fatty acids, particularly butyric, as we can see in the previous results. Moreover, Parabacteroides have been negatively correlated with weight gain, and it is of our particular interest that genus such as Lactospira and Alistipes that are increased in Ibnix chronotype subjects reduced after pistachio fermentation. Furthermore, other genus such as Rosbergia and Blautia are correlated with the expression of genes components of the circadian clock. Alpha diversity refers to the measure of diversity within a specific ecological community or locality in a given sample. It was estimated through Shannon and Simpson indexes. Pistachio fermented samples have similar results, showing the highest diversity when compared with the basal time. These results were confirmed using rarefaction curves analysis, indicating that the colonic fermentation of pistachio induced the increase of the species richness and the diversity compared with the initial time. In conclusion, the gastro-intestinal digestion of pistachio increased the bioaccessibility of phytomelatonin, which is permeable in the small intestine and possibly highly absorbed at the oral step. Besides, the colonic fermentation of pistachios favors the formation of short-chain fatty acids and other colonic metabolites that has been associated with a chronobiotic effect. Furthermore, the use of pistachios as substrate by the colonic microbiota of an obese donor with Ibnix chronotype induced changes in the diversity and richness of the microbiome, favoring the proliferation of bacteria linked to the promotion of a healthy status, including the possible improvement of the chronotype. Taken together our results, the consumption of pistachios may be a practical strategy to synchronize the circadian clocks, alleviating colonic dysbiosis and chronodisruptions, which are characteristic of the overweight and obese population. And thank you for your attention.
Thank you very much, Elisa, for this nice talk. Good afternoon.
Thank you, Steven. Good afternoon. Good morning in Mexico.
Good morning. So we'll jump into question. So the first question is about your results on short-chain fatty acids and bacterial diversity in microbiota. Were they obtained from a single fecal fermentation, so one donor? And are you planning to perform additional experiments to confirm the reproducibility of your results?
Yes, thank you. Yes, that's correct. It was obtained from a single fermentation for this experiment, but we are planning to do a clinical study to evaluate some chronological effects. And in this study, we are going to obtain the fecal samples for maybe in the future evaluated from these samples.
Okay. The second question is about the amount of short-chain fatty acid produced by inulin, inulin fermentation, that might appear low in your model. Any comment on this?
Yes, thank you. Yes, this could be for the amount of the inulin in the fermentation and the amount of the non-digestible fraction of the pistachio that we introduced to the fermentation system.
Okay. Another question is about the chewing. So how did you prepare your pistachio? Probably, yeah, at the start of your gastro-intestinal in vitro digestions.
Yes, thank you. We have the four volunteers that chewing the sample, and then they put in a base with water, and that's the oral stage.
Okay, thank you. So we have two more questions. So how many rats were used as column model?
We didn't use a rat for the colonic model. We used a fecal samples from a human.
Okay, so, and last one from the audience. Could you say what in vitro methods was used with samples? So for dialysis and solubility?
I think that is in the intestinal stage.
Yeah, I would say so. When you
I don't know.
When you mimic absorption, probably.
Yes. Yes, probably. I don't know. I think that this. I don't know.
So maybe this can be continued by.
I don't know.
Anyway,
yes.
Yeah, just I have a small question myself. I heard that abstaining from eating can also be a good way to resynchronize the circadian clocks. So would it be related in any way with the microbiota, or how can you link what you are showing and the fasting way?
Yes, I don't have idea at this time. In the microbiota, I read about the effects of fasting, but in the microbiota, I don't have idea.
Okay, but thank you very much again, Elisa. And so we answered all the questions. So except maybe the last one, but because it is an anonymous attendee, if you can complete this question, Elisa will be able to answer back afterwards. And we are about
thank you.
Now time to move on, and I will leave the screen to Didier.
Thank you very much, Steven, and thank you very much, Elisa. That was a very interesting presentation, and I have a lot of questions for you, so I will try to send them directly. Thank you.
Okay, thank you.
And as Steven was mentioning in his introduction, we would like to have more and more presentation on the relationship between food digestion and gut microbiota. So this is why we will have a specific session dedicated to that during the next conference in Cork. With well-known speakers such as Paul Cotter or Karen Scott. So if you are working in this field, you can start preparing and writing your abstract for next year conference. So we are getting close to the end, and it's my pleasure and privilege to introduce the last speaker of the day, Dr. Suzanne Bellman. Hello, Suzanne. Suzanne and I know each other for quite a long time, actually. Now she works for the team company. Maybe she will say a bit more about the activities of the company. Maybe during the presentation or afterwards, we can have some discussion about that. So today, Suzanne will give a talk on in vitro models used for microbiome research, how useful. And I hope that you will tell us that in vitro models are useful, Suzanne. So the floor is yours for a bit less than 20 minutes, and then we'll have a discussion afterwards.
Welcome everybody to this last presentation of the INFOGEST virtual conference. My name is Suzanne Bellman. I work for the TIM company, and I would like to thank the organizers for having me providing this last talk of this virtual conference. The topic of my presentation is in vitro models for microbiome research. How useful are they and what can we do with these? My first slide sets a little bit the scope of my presentation, and I am including models, colon models, that have the ability to stimulate physiological realities. I would like to further focus on non-cellular fluid models, and in my second part of the presentation, I am comparing readout parameters, and I will tell you why we focus on readout parameters in the first half of my presentation. On the right side of this slide, you see a comparison of pools of individual donors on the taxon level, and what is circled or what is having a frame are individual donors. And you can see that we have 7 individual profiles or readouts of these people. On the left side of this picture, you see the pools of it. And then you see after pooling that the composition of microbiota is getting to look alike. To start with, all in vitro models use stools or fecal matter as starting material. And as you see here, they are all very diverse. This is, by the way, unpublished data of own pool samples that we analyzed within the TIM company. So this starting material is taken from the distal colon ultimately, because this is what we have available. However, the research focuses on events in the proximal colon, but it's hard to get that because then we would need to enter people's colons, which is for ethical and practical reasons not very workable. So long story short, fecal material is the only material that is easily accessible. We can get it in a non-invasive way. And moreover, following the general microbiological understanding, though the microbial taxa vary, the metabolic pathways remain stable within a healthy population. And that is what you see on the next slide. Here you see a picture of the well-known Hüttenhauer publication in Nature of 2012, where he states that the carriage of microbial taxa varies while metabolic pathways remain stable within a healthy population. And on the right side, you see the same individual fecal samples as in the previous slide, but then on a phylum level, that more or less the variability on that level is alike in the individual people, but also the pool samples. In my next slide, following the previous one, the question arises to pool or not to pool. So here you see a representation of a publication by Copper et al. Of 2019, where fecal matter of 3 individual donors was subjected to the Scheim system. And you can see that also the bacterial composition of these donors differs, and especially donor number 2 showed different Firmicutes and Bacteroides ratio and a higher relative abundance in Acinobacteria. But despite the differences in composition. You can see on the right side of this slide that the degradation of luteolin, as was studied in this paper, was quite consistent among the 3 donors, strengthening what I said before. And the question about to pool or not to pool would extend to the question, are we needing to generate a pool, or are we generating, rather than a pool, another individual which we consider being the pool? So what I understood, or from my discussions with Jonna, who published this paper, there's basically no answer to this question. And as always, scientists love to debate about things. So there is one group of people that suggests, we would need to pool to have a representative crosscut through a number of individuals. But alternatively, not pooling would result in comparable data, as you can see here. And the same also applies to the next slide, where I want to show you a publication by Aguirre et al. In 2014, where the author also looked at pool versus not pooled material. And again, the result is the same, that the metabolic activity here measured in form of short-chain fatty acids is the same of pooled material versus non-pooled material. So I guess the answer to the question is that it always depends on what you want to see. So we've learned that the metabolic pathways do not change even though we use individual donors or pooled microbiota. Now the question, in contrast to that, arises if we look at the other way around, if we don't have healthy donors, and if we want to look at, for example, lean versus obese microbiota, which you can see in the next slide, does here the metabolic activity change? So when we have an altered microbiota, like in the lean versus obese situation exemplarily, what is the impact of that on the metabolic activity and metabolites that are performed? So in this example, lean individuals extract more butyrates, which you can see in the open triangles and the straight lines on the right side, from galacto-oligosaccharides, while obese individuals extract less butyrate from the same substrate. These are the open triangles in the dotted lines. So in conclusion to that, if we have non-healthy donors or different, so to speak, physiological situation, that in turn results in not the same metabolic activity, which is quite interesting. So circling back to the initial question, the material that we use to do colon research or microbiome research can be individual or can be pooled, as long as we use healthy donors. My second part of my presentation focuses on models, in vitro colon models, that aim to contribute to microbiome research. The next slide, you see an overview of the 4 systems that I would like to introduce to you, which is the iScreen, the ex vivo fermentation screening platform, the ARCOL, which is an abbreviation of the artificial colon, the simulator of human intestinal microbial ecosystem, and the TIM2 system. The next slide shows a little bit the specifications of each of the systems, but what they all have in common, they start with stool samples, as said, which is the only accessible source, non-invasive and easy to get. To start with, the iScreen system is an anaerobic incubation of a fecal slurry in a 96 well plate, so it has a high throughput. Factors like body temperature are simulated. However, since it is a 96 well plate, microbial metabolites are not removed, so we would call this a static system. And the initial preparation includes ileal medium as a substrate to feed the flora or the microbiota that is in the 96 well plate. The second system, the ARCOL, gets a bit more complex. It is a one-stage steered vessel. Also, body temperature is simulated, and in addition to that, the pH, very important. It includes anaerobiosis, and in this system, the microbial metabolites are removed, which is very, very important to keep a stable or healthy, so to say, balance of the microbiota. For this reason, the microbiota is dense and active, digestive, as what publications say, and it also has a supply of ileal medium included for substrate. If we move on one to the right, we see a schematic view of the chyme system. It consists of successive stirred vessels. Again, body temperature, pH are simulated, as well as anaerobiosis, very important for oxygen-free conditions. It uses active microbiota, and as shown in my earlier slide, often in a non-pooled donor approach. The removal of metabolites is optional, can be used, can also not be used. The last is a scheme of the TIM2 system, which is, in contrast to the earlier systems, not a stirred vessel, but a compartmental system, which has a peristalsis included, allowing to sort of move around and mix and squeeze the fecal matter. It includes, just as the others, body temperature and an active pH monitoring, anaerobiosis, of course, and importantly, standardly, microbial metabolites are removed. The microbiota as well is dense and active. And again, the standardized ileal effluent medium is fed or individual substrate in order to understand specific substrates. In the next slide, we are now looking at readout parameters. So I was trying to compare control experiments of all these 4 models, first of all with the golden standard of humans. So we know not much about the situation of the proximal colon in humans simply because it is difficult to access. However, we do know that the bacterial density is 10 to the 12th. We know an average of short-chain fatty acids are produced in the proximal colon of about 123 millimolar. And we know what an average short-chain fatty acid ratio is, which is 60-20-20. And of course, that depends on the substrate or on the food that we eat. Now I've tried to compare this with the iScreen, Arcol, chyme, and TIM system with regard to these parameters. Again, the context for the iScreen is rather a screening tool. I was not able to find exact bacterial counts and density, but literature says it is high. The short-chain fatty acid concentration was also a bit higher in the iScreen, likely because there is no metabolite removal integrated in the system, which also ultimately impacts the short-chain fatty acid ratio. The adaptation period for this system was given with a day. The Arcol system, which is a single beaker, has a bacterial count of 1 to the 7th, so we are coming close to the one in humans. It has a dialysate that removes the short-chain fatty acids, which the concentration over time was given with 9.4 millimole per hour. And also the short-chain fatty acid ratio comes close to what is found in vivos. The adaptation period increases in this system to 3 to 4 days. The chyme system, as mentioned, has the possibility to run experiments in parallel. Also, the bacterial count is increased even more towards the physiological situation. However, the short-chain fatty acid concentration was reported with 56.4 plus minus 13, which is a bit lower as what we observe in humans, and that could be related to the a bit diluted bacterial density in the beakers. While still we have a physiological short-chain fatty acid ratio, a big drawback is perhaps the adaptation period of 14 days, which is quite long. And then last, the TIM system has also the possibility for parallel experiments in the 4 cabinets. The bacterial density is high and reported to be higher than 10 to the 10th. Shows a physiological concentration of short-chain fatty acids produced and a ratio which is again close to what we see in vivo with a very short adaptation time of approximately 16 hours. In conclusion, all colon systems use fecal material as a starting material because that's easy to access. Whether or not to pool it is still the question which remains. pooling or not to pooling from healthy individuals is certainly to do, while we have to pay attention if we pool material of deviating or non-healthy donors because their metabolite profile might deviate. However, if we want to, and that accounts for all in vitro models, if we want to have physiological relevant data generated, we need to mimic as much as possible the physiological conditions as they occur in the colon, which is including an appropriate microbial density, which is including the removal of metabolites, which is including feeding a substrate that is representative for the ileal effluent that we find, and which also includes molecular pH monitoring so that the environment we want to simulate is exactly the way we find it in the colon. Thank you very much for listening in. Thank you very much for visiting the INFOGEST virtual conference. I hope you liked the presentation and looking forward to be in touch or to meet face to face as soon as we can. Stay healthy. Bye.
Wow, very nice music. Thanks a lot, Suzanne, for the interesting presentation. I have a look at whether there are some questions. Not yet, so I will start. I was really interested by your presentation to see the diversity of models that we have for for mimicking what happens in the colon. It's very similar to what we have for the upper part of the gastrointestinal tract with static model, dynamic models, and most of the model I didn't know about them, especially the one that you call the eye screen. I didn't know that there was this kind of model. One of my questions regarding the TIM2 is how do you maintain anaerobiosis with this system? Can you explain me, because I'm not an expert in colonic models, so if you can explain how do you do that, that might help. Thank you.
Mm-hmm. Yeah, thank you for your question, Didier. Actually, very simple. The units are just closed and we do flush them with nitrogen. So basically pushing out everything which is oxygen, containing oxygen. Yeah.
Mm-hmm. Okay, and I was really amazed by the adaptation time that looks extremely low for me. So mm-hmm. it's good. It's good because I guess that you can increase the number of analyses that you can do, number of experiments that you can do within a week. Yeah. At the moment, do you know how many, more or less, how many experiments you can run with the system, let's say, every week?
Yeah, so as said, the adaptation period is about 16 to 24 hours. And with the units in one cabinet in parallel at our lab, we have 6 units present. So we can run 6 comparisons or 3 comparisons if we do them in Duplo, for example.
Okay. So I have now a lot of questions, so I will try to, I will ask you to answer quickly. First is from Andrea Gianotti. Hello, Andrea. What do you think about the possibility to set up a mock community representing fecal inoculum? Realistically feasible?
Question mark. Yeah, that's it's almost a philosophical question. Yeah. So yes, of course, it is possible. But, you know, given the big variability that we also see in vivo, the first question would be, what would be such a mock community? But yeah, of course, it's possible.
Okay. Next one is from Patricia Ruas Magliedo. How easy will it be to include the host cells, for example, Keiko2, into these systems?
Yeah, that's a good question. And you know, I did focus my scope on non-cellular models, but ultimately, of course, absorption needs a gut wall, needs cells involved in order to have a translocation. And what we sometimes do, we combine material that comes from the system with intestinal segments. So these are small gut explants from either the small intestine or the colon, and then we subject dialysis material from our system to these little tissue materials, and then you would look at translocation.
Okay, Another question on the adaptation time. How do you explain the differences in adaptation time between the TIM system and the other system? Do you have an explanation for that?
Yeah, that's important also. I guess the main point is the membranes that remove metabolites that are formed, so that the environment in which the microbiota remains sort of physiological or stable. But if these membranes are not there, and if the metabolites that the bacteria constantly produce, if they pile up, then the bacterial community is changing in response to these piling up metabolites, and that will take time for the microbiota to sort of establish a new balance or equilibrium, which is ultimately then more related to the circumstances that are there rather than the physiological environment.
Okay, another question is that most colonic models look at the fermentation of a product fed directly to them without pre-digestion in gastric and intestinal phase. What can you say about that? Is it relevant or not?
Sorry, can you repeat the question? Laura?
When you put directly the compounds that you would like to study in the colonic model without the gastric and intestinal phase, is it relevant or not? What do you think?
Another philosophical question. Yeah. Of course, pre-digestion removes material that naturally would not occur in the colon. So if we don't do a pre-digestion, then we have to take into account that whatever is digestible is the easiest for the bugs to eat. And that would mean that they start fermenting things that would not be in the colon in the first instance. But you could go right into the colon if you start working with fibers, for example, that are not pre-digestible, not digestible.
Yeah.
But also there, the question is whether or not these fibers are modified by a pre-digestion step.
Mm-hmm. Mm-hmm. Another question about the adaptation. Which is the top parameter that you use to define that the adaptation has been reached?
We, for example, online monitor the pH, and we see, so we do maintain a certain pH, which is representative for the colon, and we do see how quickly and how slowly these bacteria sort of ferment, and when this is a sort of a stable line, we know they are adapted.
Okay. Thank you very much, Suzanne. There are at least 5 or 6 more questions, so please have a look and try to answer this question. Thank you very much. I wish to thank all the speakers for this last session and my colleagues who co-chaired the session with me. I see that André is ready to hand over, but I would like to say a few words before. Yeah, I know we're running out of time, but I wish to warmly thank all the people from the Tagash who organized this event. This is the first time that we had this virtual conference, and I think it was a great success. Thanks to you, André, Linda. Again, I wish to thank also the postdocs from TIGASC. The session we had yesterday evening was fantastic, and it was run perfectly well. And I wish to thank all the participants for being present. So, André, I leave you the floor for the conclusion and the awards.
Excellent. So I just have a couple of final remarks. I think we have seen enough slides, so I stay away from any slides. I would like to thank all speakers and all the session chairs, and also the organizers behind the scenes. So there's Maren Egan, who's doing all the magic of the webinar, and she's also handling the YouTube videos. So all talks will be uploaded onto YouTube later on. And I would also like to thank Nathalie Lamar in the AgroCampus in Rennes for the organization. That was really valuable. We couldn't do it without you. Overall, we had a lot of live attendance. So the maximum number was about 360 yesterday. Today we were around 200 between live here on Zoom and YouTube, and I could see people coming and going, and that is the whole point. We didn't have a lunch break because everything will be recorded, so you can watch the talks later on the YouTube channels. 6 continents. We had live attendance from 6 continents, so a true global events. And I think that really, that online platform now really democratized the conferences in many ways. So just 2 last things. This was a free conference, so it was organized, let's say, in our spare time. We didn't have any sponsors. The last talk, Susanne Bellman, they agreed to sponsor the prize for the best oral talk. But next year in the physical conference, we urgently need sponsors. So physical conference, they are much more expensive to run. We can't run it on a shoestring, just as this event. So last but not least, before I hand over to the prizes, the poster session last night, our postdoctoral team here in Moorpark, they volunteered. They ran it completely on their own without any input from us. And I think it was a super event. It ran like a well-oiled machine. And that usually means that a lot of organization went in there. And that was pretty visible. I enjoyed attending it, and I watched it on YouTube. I was outside, and that was actually pretty good. It's a good format. I think it put the speakers under pressure to put everything into 3 minutes, and that is a task. You know, how do you tell a good story in three minutes? But I think they did a marvelous job, and that's probably something to think of for the future as well, to integrate something like that on top of the poster session or something like that. So I would like to hand over to the postdoctoral team and Guldan Goxon. Oh yeah, show yourself first of all. Excellent. So you see everyone on the screen now. Thank you all, and I hand over to you, the postdoc team, for the first prize.
It is very difficult to select one flash presentation. They were all excellent, nicely prepared and presented. We wish we could award more of you, but it is not possible. So the best flash presentation of the virtual International Conference on Food Digestion 2021 goes to presentation number, are we excited? F11, Katerina Palchim from KU Leuven, for her presentation on moving towards more complex static in vitro digestion condition to evaluate macronutrient digestion of the chickpeas. The differences between simple and simpler. The award is paid registration fee for the next year's INFOGEST conference in Cork, Ireland. Congratulations to Katerina.
Andre, you're on mute.
As usual, it's my favorite sentence, yeah? You're on mute. So Miriam Grundy and Elena Ahrens, if you can show yourself. They were the judges for the next prize.
Yes, the same. The quality of the presentation was really high. So we had really a difficult task to find the winner. So yes, we judge the presentation on the slides, the quality of the slides themselves, the oral presentation, the overall structure of the presentation, and also the answer to the numerous questions. So Elena, would you like to say something as well?
Thank you very much, Marianne. It was great honor to be participating as a judge during the last 2 days. It hasn't been an easy task. All the presentations were standing, and of course we had to decide one, but just highlighting that's great job to all, and best of luck with your studies. Thank you. All over to Susanne.
Okay, so to me, the honor to announce the best PhD talk. And the winner of that is Joanna Nadia from Reddit Institute in New Zealand with her talk, The Effect of Food Structure on Starch Hydrolysis during gastric digestion, gastric emptying and glucose absorption in vivo. Very, very much congratulations from all of us for your lovely and wonderful and most importantly, interesting presentation. I'm not sure if you're online or if you're maybe sleeping over your award, but congratulations from all of us and especially from the TIM company.
Over to you, Linda.
Okay, so I'm going to ask everybody else except Natalie Lamar and Warren Egan to turn off their cameras, and just Natalie and Warren to turn on their cameras. So we specifically want to thank you guys, Natalie and Warren, for all the work that you've done in the background with INFOGEST. It just wouldn't exist without Natalie, and from Warren for being our webinar support. And we've really been learning on the job over the last few days, and Murren has been there every minute of the day in the background, running the videos and broadcasting on YouTube and recording and everything. So we want to thank both of them really sincerely. So thank you guys.
Thank you for this kind attention.
And so nextly then, and lastly, I want to thank Andre. So Andre, yes, there you are. So I want to thank Andre for saying yes to this conference. We have worked in different departments in Teagasc for many, many years, and we have a large number of projects in which we collaborate on, and it's a real privilege to work with Andre. I would say that his strengths are, and these are strengths that you need for running a virtual conference, is his calmness, his fairness, and his sense of humor. So thank you, Andre. So I'm just going to finish up with a few quick things then. So one of the passions of mine is gender balance and gender equality, and encouraging young people in science. So the speakers were selected on their scientific merit of their abstracts, and that was done by the working group leaders within INFOGEST. But if you now look at the stats, you can see in retrospect, you can see that of the oral presentations, we had 19 female presenters and 9 males. And in the poster, we had 17 females and 7 males. So that's the stats for this virtual conference. Finally, next May, please remember us and come to Cork next May. I think Murren will be putting up a holding slide at some stage. So if you can do that now, Murren, that would be great. As Andre said, we ran this webinar on a shoestring, but we will need companies to support us going forward into a real life in-person conference. So that's it. I think I'm going to close the conference now, unless Andre and Didier want to say anything. No, you're all good. So I'm going to close it in Irish. So Garamí and Machagav Galer agus Slán live.